All right. So welcome to the last session of PETS. We are finishing with 4 papers under the topic of attacks. That is the topic of the session. And I'm Claudia Diaz. I will be chairing the session. And our first paper will be presented by Dionysis Manousakas with the title Quantifying Privacy Loss of Human Mobility Graph Topology.
Hello, everyone. So this is a work in the anonymity properties of graph representations of longitudinal mobility. Nowadays, large volumes of location data are being continuously collected by localization-enabled devices that allows us to derive valuable personal information which we can use in enhancing context awareness of mobile services, and also they add a lot of information that can be used in large-scale analytics in transportation management, healthcare studies, urban development, etc. Thus, researchers have pursued for privacy preserving anonymized data representations of the data of this information, and they have all many times released it in forms of histograms, heat maps, or graphs instead of the initially collected timestamp data points. However, it's largely under question how privacy conscientious each of these representations is, as each of these representations leaves certain privacy-sensitive patterns of the data intact, and thus require a separate process for sanitization. There have been known privacy breaches on mobility data, which have led to a lot of studies during previous decade. So mobility was attacked by exploiting sparse and regular patterns that are inherent to this data, and has been achieved by using top-end location information, a few spatiotemporal data points, or matching mobility of users in different observation windows just by using histograms of their routine. Also, people have fitted probabilistic models in historical mobility data and have used them to de-anonymize by maximizing the likelihood of unlabeled data, or minimizing the distance of transition matrices describing person's mobility or the stationary distribution of these models. There has also been sought a solution to this anonymity leakage issue via using aggregate information in studies instead of individual information. But there has been a lot of recent work showing that we can infer sensitive information even on the basis of population statistics. Namely, we can recover individual trajectories without priors from aggregated mobility data, and also we can aid the priors of adversaries by releasing aggregated location time series, even perturbed under differential privacy mechanism. So let's see what we do in this study in particular. We start from raw mobility data, which are timestamped GPS data points. and we gradually remove information, first by clustering in the spatio-temporal domain and recovering regions of interest, and then by removing the geographic information and representing those regions as states in an abstract space, and also removing the timestamp information and just keeping the ordering of transitions. Close to this scheme, there have been releases of data recently, for example, in the Nokia Mobile Mobility Data Challenge research track, and also in the Device Analyzer dataset. We can all for sure agree that the storage costs get greatly reduced, which is great because those representations can fit on mobile devices. Utility gets generally reduced, however, there is a lot of information that still is maintained, and this is under the control of the data publisher. Inference difficulty gets greatly increased as more of the as all the aforementioned attacks are not viable in the latter setting. However, what exactly happens to the privacy loss of this structure? So that's what we study in this work. Let's remove all cross-referencing information consisting of the timestamps and the geographic information of locations, and let's just keep the connectivity of locations in users' longitudinal mobility and the regions of interest as abstract states in a graph. And let's try to answer what's the privacy leakage of this representation if this connectivity still bears enough structural information that can allow us to exploit it in a de-anonymization attack. This is how mobility information flows in our study. We start with raw mobility data. We design a graph representation by removing cross-referencing information and doing some predictable order selection of the graph. And then we detect privacy-related patterns on this graph structure, and we finally evaluate the privacy loss by designing an appropriate de-anonymization attack scenario. The data used in our experimentation are a subset of the Device Analyzer dataset, a dataset collected from many countries with more than 30,000 participants, having system information and localization information as cellular and Wi-Fi access point information. For each cellular identifiers are pseudonymized per handset. From this, we mined 1.5 thousand users with the most cellular location data points, which resulted to an average of more than a year of observation and more than 200 regions of interest per user. We defined graphs, mobility graphs, as graphs with nodes corresponding to regions of interest and edges to the recorded transitions over the observation period. This was defined on sequential data by applying a network order selection technique to find the optimal order of Markov chain that can describe those data, which was consistently 1 when considering more than 20 locations. We also allowed node attributes corresponding to a categorization of the locations according to their frequency in users' mobility routine, edge weights corresponding to the absolute frequency of recorded transitions, and we also did part of the analysis by pruning the networks to the top n visited locations and defining what we term as top n networks. The statistics of the graphs in our dataset showed that we have heavy tail degree and edge weight distribution. To analyze the privacy properties, we generalized k-anonymity to populations of graphs via graph isomorphism, defining that the population of graphs satisfies this property if it's separated in isomorphism clusters with at least k-member seeds. We found that in our population of 1,500 users, 20 locations are enough to assign each individual to a separate graph, which is a bit higher, corresponding to the upper bound, to the theoretical upper bound, which is the network size required to generate enough non-isomorphic graphs to cover our population, the population of 1,500 users in that case. But we also found that anonymity is fragile even when considering less locations, and median anonymity becomes 1 even for less than 10 locations in user's profile. So we found enough structural diversity that allow us to say that each mobility graph is distinct, but can we exploit historical information provided as a graph to de-anonymize? For this, we also need some repetitive patterns of the users among different observation windows, and for that we got empirical evidence. This is the profile of a typical user, and we can see some of the 20 most visited locations over the first observation period and the respective locations in the second half of the observation period, and we can see a lot of overlaps of the edges and the nodes that are present in his mobility profile. We then describe the threat model to get a quantitative grasp of the privacy loss. We consider the closed world of users, and we split their observation periods randomly in two. We consider that we have access to the identities of the one population of networks, which we get, but we have no access to the other one, and this is what we try to learn by associating the structural patterns of the two populations. So an adversary tries to de-anonymize each of the networks of this population by using the knowledge of these networks. In the case this adversary has no access to historical data of the user, the best he can do is to simply assume, to simply assign randomly identities to the unlabeled networks, which give us expected rank for the true identity of the network equal to half of the size of the population. An adversary that has further access to historical data for the user, he can try to update this categorical probability estimate that he maintains by assigning more probability mass to identities that have displayed higher structural similarity. For this, we had to evaluate pairwise structural similarity with a population of labeled networks, and then we can just pass this through a non-decreasing function and normalize. This will give us a legitimate probability. And then we can quantify the privacy loss just by taking the ratio of this posterior probability over the probability of the uninformed adversary. To quantify pairwise similarity, we used graph kernels, a standard technique for quantifying similarity of objects in machine learning. In that, each graph is expressed as a fixed vector of counts of atomic substructures on the graph. Such can be graphlets, shortest paths, or Weisfeiler-Lehmann trees, and we can further compute deep versions of those kernels, which additionally learn encodings of the atomic substructures and are more robust to small variations at the substructure level. So then we updated the ranking of the identities of the adversary after computing these pairwise similarities, and this is the CDF. The uninformed adversary would have a CDF lying on the diagonal, while the adversary, using some of the kernels that we used, has managed to improve this estimate. We got the best performance by using the deep shortest path kernel defined on the top 200 networks of the users, under which we got a mean correct rank at 140 as opposed to 750 for the uninformed adversary. When using the inverse rank for the F function, which the adversary used to update this probability, we got a median privacy loss equal to 2.5. We realized that location pruning does not necessarily enhances the privacy of networks when this is respecting the frequency of locations in user's profile, that including rare transitions add more noise than discriminated information. However, the anonymization is assisted by using the frequency information of locations and directionality of transitions. So to sum up, we showed that graph representations of longitudinal mobility show distinct structure even when considering a small number of locations in user's profile, that less than 20 locations are enough to uniquely identify a population of 1,500 users at the level of cellular location information, that we can devise kernel-based distance function and quantify similarity in the absence of location semantics and fine-grained temporal information. And this can allow us to devise an adversarial mechanism for de-anonymizing that has 3.5 times higher median success probability rate compared to an uninformed adversary. Thank you very much.
Questions? Do we have the other microphone charged? Great.
A couple of questions.
Yes.
So first, if I understood correctly, neither your nodes in the graphs nor edges in the graphs have any kind of weighting, right? They're just graphs.
Yes.
And secondly, if they're just graphs, did you try to work out what is the information loss coming in from just choice of nodes versus adding in the edges as well? Do you see what I mean? Where is the information coming in?
We cannot match nodes among graphs. Each
Right.
node is an abstract state, which is on a user-specific kind of system of coordinates. And also, we do not have weight on the edges, on the nodes. However, we can assume a categorization of nodes. So we can assume a category of very frequent locations and a category of rare locations. And this can be this can be found by using just the sequences of states. So we don't need any additional information for this categorization.
Is there a question there?
For the users that you choose for the, did you check if they share a fair bit of their mobility, or did you choose your data set and your user?
We choose the users with the most location data points in our data set. So we try to find users with long traces.
But you say that the study was in different countries, so you have people from different countries, or
Yes.
for the same city? Okay.
But all this location information is just they are just hashed discrete. They're just hashed natural numbers, yeah, these are just states. They do not have any kind of geographic underpinning.
Yeah, but still you might, depending on the city where you live, the mobility patterns could change, because I don't know, the mobility pattern in Barcelona, even if you don't have the geographic information, will be different than in Tokyo.
So this analysis is agnostic to all these parameters. We do know that we apply the data on at the cellular level at cellular localization, but we don't have any other information.
So you didn't try to do it on a part of the population which is in the same city? And,
No, we don't
see-
have any kind of demographic information in our data set.
Yeah, if I may follow up. So the thing is that you have diversity of provenance of this. So these are different cities,
Yes.
different locations. So one could imagine that in Barcelona, there's a population mobility and many people share mobility traces, in the sense that if you had your several thousand traces all from the same city, maybe you would find that there are more similarities because people tend to move in the same ways in a certain space. In Barcelona, the mobility trace might be more similar between two people living in this city than one living here and one living in some village in Germany, right?
Yeah. In fact, this gap of our empirical finding from the theoretical upper bound indicates that there is a kind of sharing of global patterns in the mobility graphs of users.
What do you mean?
So I mean that here we find how anonymous are the graphs in our population, and we find that this is higher than the theoretical upper bound for anonymity, which means that many of the users in our population share structural patterns, and we require to take more locations that the...
No, but the question is that you're about the data set, right? Like if you had a data set that was more homogeneous,
Yeah.
in the sense that it comes from the same city, that could have an impact on the results, in the sense that you would have more similarity between graphs. because people in the same towns tend to go to the work area or residential area or leisure area. There's more overlap.
Yes. So we couldn't check the geographic distribution of our participants in the dataset because we do not have this information in the dataset.
Okay, so you couldn't check if there was a difference that people in the same locations would have more similarities?
Yeah, we couldn't check that.
More questions? Someone here?
How do you think the results would vary if the datasets were much bigger or slightly smaller? Like, what is your intuition on, like, is this applicable to, not thousands of people, but millions of people?
In terms of the efficiency of the de-anonymization attack. So we expect that long traces enable the adversary to de-anonymize easier because we can have a more fine-grained categorization of locations. And we expect that very short traces will make his job much harder.
I have another question about, so you have this use case in which the adversary gets this graphs that have no location information,
Yes.
geolocation information, or time. So what is the use case for, what would you use these graphs for in a kind of legitimate use case that?
Yeah, for example, this could be a data structure which we use to store mobility on mobile devices. So it's kind of a summary of the.
But why would the location, the geographical location, be removed from those nodes? What use case do you have in which you want to have a large data set of unlabeled location graphs? What kind of analysis would you do with that?
Yeah, so our initial motivation was to do an analysis related to healthcare, to like Alzheimer patient mobility patterns, and yeah.
So in-house, you mean?
And outdoor.
Outdoor as well.
As well, and so we expect that there will be visible differences in the.
And there you do not need to know this is the kitchen
Yeah,
and
yeah.
this is the bedroom, but just whether they are moving.
Yeah. So we remove that for anonymity and also for storage efficiency.
Okay. More questions? No? Let's thank the speaker then. So this second talk will be given by Michael Freiberger, and the title is Cracking ShadowCrypt, Exploring the Limitations of Secure I/O Systems in Internet Browsers.
Awesome. Thank you very much for that intro. So I'm Michael Freiberger. This was joint work with two of the primary authors of the original implementation of ShadowCrypt, Warren and Dada, Michelle Mazurek from University of Maryland, and my advisor, Pratik Mittal. A little bit about me, since I'm not currently a graduate student. This was my senior thesis work during my undergraduate at Princeton University, which I completed in 2016. And for the past 2 years, I've been working at AppNexus as an engineer, and I really like to wear hats. So the motivation for this work is that user-provided textual input should be hidden from web applications. So we talked about secure messaging this week, and when people are communicating back and forth with others, we want that to be secure. But there are plenty of applications where you're more or less communicating with yourself with a few extra features that are offered by the web app. So for instance, when I'm using a calendar application, I'm typing in the title, but Google really never needs to know the title of my calendar, like an event, in order to have a correct functionality. And there are a bunch of other applications like this. So to-do list applications, when I'm creating a to-do list, really all it is me talking back and forth with myself with maybe a checkbox for complete or not and a due date. Similar to calendar applications or sort of online notes or journals where you're maybe tracking what you did that day. An important note is the applications still need access to metadata, such as whether or not a task was complete, the due date of a to-do list item, maybe the start time and end time of something on your calendar. But these applications do not need any textual input. A calendar doesn't need to know the title. A calendar app doesn't ever need to know the meeting notes for that particular event. So ShadowCrypt, in 2014, they published a paper at CCS where they attempted to provide a solution for this. So they wrote a browser extension that would scan the page for all of input nodes and transform those input nodes into secure input nodes. And what I mean by secure input nodes is they were utilizing the Shadow DOM, a new primitive that came out to browsers probably around 2013, 2014, that allowed for a separation between client-side code and then potentially where the data is actually rendered. So from a user interface perspective, what would happen is if you had a web app where you're about to type in your homework for that week, if you were using ShadowCrypt, instead of just having a plain input, it would look something like this. The user would be able to see, oh, this is secure. And what's happening under the hood is ShadowCrypt is parsing the DOM, and they're finding all of the input nodes, and they're also finding all of the output nodes that have a ShadowCrypt fingerprint. And they're taking those input nodes and they're attaching a shadow tree. And in that shadow tree is where the user will actually interact. So when a user is filling in their homework for that week, they'll be interacting with that bottom blue square, and the gray square, which the web application actually has access to, would only see the ciphertext, and all the encryption would happen within the shadow tree. And similarly, for any output, ShadowCrypt would recognize, oh, this was encrypted, let me create a shadow tree in order to do the decryption and actually display the plain text. So that's what ShadowCrypt does, and our paper is attacking ShadowCrypt. So we have a UI-based attack, and as well as a Shadow DOM penetration attack, and I put attack in quotes for reasons that I'll explain later. The UI-based attack. Some fundamentals of the attack is that the attacker is the web application itself. So I, as a web application, am aware that users are potentially using ShadowCrypt. All of a sudden, I'm not getting access to all these calendar titles that I want to share with data brokers to get more ad revenue, whatever it may be. So I'm like, oh, I don't want ShadowCrypt, so let me add code to my client side to be able to prevent ShadowCrypt from working. And so that's exactly what ShadowCrypt is doing. They're trying to update their client-side code such that they can actually gain access to this user-provided text. An important note is that this attack must be stealthy. You can imagine an attacker could pretty easily do some sort of DOS attack. A simple DOS attack would be finding all of the elements, or even they could, on their API level, if they ever get an input with some ShadowCrypt fingerprint, they would easily be able to potentially just delete that and just not allow users to use this. But users would pretty quickly realize, like, oh, this website is fishy. Why are they not letting me use this browser extension that's providing me security? So as an attacker, you need to be stealthy such that the user freely gives you the information. The user thinks ShadowCrypt is working when in fact it is not. So what we did is we built a web application. We built a to-do list application that a user could use. We then updated that client-side code such that we were attacking it. And then we validated that attack through a user study to figure out whether or not a user could actually tell if this application was attacked. So to go through our user interface attack, I want to highlight the different steps of what ShadowCrypt actually does, and then how we sort of systematically took them down one by one. So the first thing ShadowCrypt does, as I said, is it will transform all of the editable content fields into secure input nodes. And so naturally, if I am the website owner and all of my input nodes are always secure and I'm never getting access to plain text, I can't actually execute any sort of attack. So the first step is getting an insecure input node onto the page. And by that I mean I need to bypass the ShadowCrypt's input detection. If I can have something on my page that ShadowCrypt doesn't think is an input, they won't actually attach a shadow tree, and therefore I can gain access to the user's plain text. So there are a few different ways to do this. The simplest way is just that ShadowCrypt isn't actually looking for inputs with type search or type email. There's actually important reasons for them doing this, is because, as we talked about earlier, search is actually very hard to search encrypted data, and so therefore ShadowCrypt doesn't want to decrease the usability, and so when someone's entering in a search bar, they're like, oh, we shouldn't encrypt that because they should probably send that to the browser, send that back to the application in plain text when they're doing a search. So they don't actually ever detect search nodes. Similarly, email nodes, because it would be very hard to log in if you once registered with an email in plain text, and now all of a sudden you're registering and trying to log in with an email that's encrypted. Also, it would be very hard to get that first email to confirm your identity. So you don't want to be encrypting email stuff. Now, you could think, let's just have ShadowCrypt have a few more false positives. Maybe the user can like select themselves. Okay, let's turn that off. But they're sort of right now going on the side of, we'd rather not have any influence in usability, and they don't want to decrease the usability of the site. So another way to do this is, there's some DOM events they're currently not listening to. I could just set up a checkbox input field, and they naturally wouldn't do anything with that because checkboxes are just binary on and off. And then I could just write a script, change the input type to text after the fact, and they're not detecting that DOM event. Pretty easy for them to just patch that. The last one, which would be really, really hard to do in order to actually ever mitigate, and this is a really strong attack, is that a lot of websites aren't actually using just standard inputs like the HTML type. They're using input-like elements. So Google Docs isn't just one massive input. It's like a very complex structure with a bunch of event listeners registered on keystrokes, and it'd be very, very difficult for any sort of implementation that's trying to provide this to actually take all that and then effectively re-implement everything inside of some shadow tree-like element. So we can be pretty confident the attack can get past this and can actually bypass ShadowCrypt input detection. So all we've done so far is gotten an insecure input node onto the page, but that's really not great because the user would pretty quickly realize like, oh, why doesn't this look the way I would expect it to look? Because ShadowCrypt provides this nice UI, and they have this nice lock, and they have this nice border with a color, so I as a user know there's nothing fishy going on. And so I as an attacker naturally need to mimic that secure UI, so the user thinks it's working. Now, mocking the UI would actually be pretty complicated. The lock has some fancy JavaScript on hover stuff. They have really nice animations. I didn't want to try to mock that. Also, like there could be this color. I didn't actually know the color of it, so therefore it would be really hard to guess that color correctly. And also, if they change their UI ever, it would be really hard to maintain the attack. So it'd be much simpler if I could just render an insecure node directly on top of a secure node such that the user thinks they're interacting with a secure node when really they're not. That's a much simpler way as an attacker, just a few lines of JavaScript rather than a lot of hair nesting. So what I did, it looks like this. Sorry if you can't read this, but I'll explain every single element. What we have here is on the top, this attacker input, which is type search, which ShadowCrypt doesn't ever detect. And then below that is the actual input with type text, which ShadowCrypt actually sees, and they thankfully go ahead and give me this beautiful UI, and then I just smack my insecure one on top of it, and I can just use CSS to make sure that it's on top using like Z indexing. And now, when a user clicks into it, they're clicking into my input, which is not secure, and it looks just like ShadowCrypt is working. This is great. Now it's pretty stealthy. There's a few more though. ShadowCrypt provides some sort of like, almost like a challenge to the attacker in a way. When a user clicks into this, the ShadowCrypt border will become thicker. And so I, as an attacker, then therefore need to mimic that because I don't have access to their CSS code, it's living in the shadow tree. So it's like, well, this isn't good. So what I'll do is I'll just render a colored rectangle and put it in the right place. I know exactly the width of this input, and I can just put that colored rectangle directly where it needs to be. Now the issue is I don't actually know the key color. The key color is a user-provided field that all of the key options are stored locally in local browser storage, and I don't have access to that. Thankfully, it's only 1 pixel, and I'm sure no one in here can tell the difference between these two pictures. The top is a 2-pixel green border, which is benign, there's no attack, and the bottom is if the user had a green border and I just naively guessed a purple border as the color, and you know what, I got it wrong, but I'm pretty confident users won't be able to tell. And so now we're doing pretty well, and the last one is actually a really tough one for me as an attacker, is that ShadowCrypt provides a keyboard shortcut which allows for input in a pop-up window. So some more details on that is we have ShadowCrypt, when a user hits control backtick, it will pop up this window where a user can input, and on that window, it's really important, see the highlighted area there, is this passphrase. So similar to how a user can select a color, they can also select a passphrase, and that's anything. Color, there was only 6 options. Passphrase, it's infinite. A user can type in anything. And I don't want to go about trying to guess this passphrase because I'm pretty confident I'll get it wrong. And therefore what I'll do is if the user ever hits control, I'll just turn my attack off. I'd much rather not be detected and only get a percentage of input than ever be detected. So that's exactly what I'll do. I'll just be like, I don't know the passphrase, let me just turn the attack off if I see a control key. So we're doing pretty well so far, or at least I think so, but that's not actually convincing necessarily. So we put a user study on Mechanical Turk, and basically the steps were, first we would have the Turker become familiar with this to-do list web application which I created. It was more or less just the standard Meteor to-do application, so I didn't have to write much code. But users aren't familiar with this, I want them to become familiar with the application so they have a knowledge base of how this actually works. Next, they become familiar with ShadowCrypt. I created a video where I explain exactly how ShadowCrypt works. I explain how all the options work, how to set up the options. So that the Turker isn't naive. We try to give them as much knowledge as we can. So this is a more conservative approach because most users wouldn't really know all these options, but we try to be as conservative as we can so the user knows ShadowCrypt. And lastly, we show an experimental version of the web application to this user, and there's a 50% chance of the application being attacked. Our study involved 105 participants. 46 participants were in the control group where the application wasn't attacked, and 59 participants were in the experimental group. So our results. Only 1 out of the 59 people noticed the attack. This was pretty good. I was expecting this because you would have to change the color and you'd have to recognize that color was different. And then the other part is we turned off the attack whenever they used that really secure input node. And so I wanted to see how much of this plain text did I actually capture. And so 92% of the inputs were just inputted plainly. They weren't using the more secure input node. 8% were, but still as an attacker got 90% of the text provided by my user. So I'm feeling pretty good about that. So what are our insights here? The biggest one is detecting and alerting users of this UI misbehavior is really important. The authentication mechanisms that were put in place by ShadowCrypt, they were either easily mimicked or they were just too difficult to use as a user. So as a user, you weren't going to use that control tick very often. You just want to be typing in content. So therefore, they were never really using that. And therefore, I was able to gain access to a lot of the plain text information. Another really important one is privacy systems should really not rely on passive in-content indicators. Users are very prone to ignore these, not really know what they mean. And so it'd be much better if we had systems that could detect these sort of DOM overlays. All I did was simply put something on top of something else, and that really shouldn't be allowed. And so we have some promising work right now that was put out a few years ago by Kaminsky called Ironframe, which is detecting these DOM overlays. And it would be great if we could really alert our users, rather than having something that's always either red or green that they should be looking at to see if something sketchy is going on, really bring it to the forefront for users to know that there's some UI misbehavior going on. Now, all this attack assumed the shadow DOM was actually secure. And so did I actually need a UI-based attack, or could I just go right through that shadow DOM boundary? So I come back to the slide I had earlier, which supposedly said that I, as an owner of the application, can't pierce down into those shadow trees. So pretty quickly, I just wanted to test that out, and that was not true at all. I very easily was able to just access directly through down to the shadow trees to get the plain text information very easily. Now, that's nothing to say against ShadowCrypt. The important thing here is Shadow DOM is not a privacy primitive. It was implemented to make UI developers' lives easier, and so therefore, it has changed over the years. Client-side code can access this stuff very easily now. And when it was written back in 2013, ShadowCrypt implementers were actually be able to create that secure boundary, but since the spec has changed, it is no longer actually able to secure that boundary. So what we need are privacy-enhancing browser primitives. We need something that can actually provide an impenetrable barrier between application code and the content that the browser is rendering. The closest thing we have right now is an iframe, so you could think of, okay, maybe we can have an iframe-based solution that actually provides that really strong barrier, but iframes have a ton of limitations. As I said, they need to decrypt all of those output elements. So if you have a to-do list with 100 things, that's going to be 100 iframes. The performance there is going to be seriously limited, and so we need a more dedicated browser primitive that can allow for client-side code to be disconnected from the content that's actually being rendered by the browser. So last slide here, key takeaways. I think the most important thing is just recognizing that this is pretty important. I think we're so constantly talking about secure messaging, which is definitely really, really critical. And I think potentially the next step is some of these applications where you're effectively just talking to yourself. So to-do lists or calendar applications or different online note applications, such that we can have secure input-output systems on browsers. Secondly, UI attacks must be prevented actively rather than through passive indicators. And we really need a secure I/O system that's backed by dedicated browser primitives rather than trying to allow for privacy system engineers to just be sort of trying to hack something into something like the Shadow DOM when it really wasn't fit for that. So the user study with all the questions I asked are online, as well as the code for where I attacked this to-do list application. Thank you very much, and I'm glad to take questions.
Questions?
So does the website you're visiting have to know anything about ShadowCrypt?
Yeah, so the website I implemented definitely knew everything about ShadowCrypt. ShadowCrypt is an open
that's
source.
in the attack, but
Yeah.
normal use of ShadowCrypt.
Normal use, no. It's a browser extension, and so like you could install it now, and you could go on Facebook, and all the content you write would become secure.
So how does ShadowCrypt know that, like, if you type something on Facebook, say, it's gonna end up encrypted, and then when it shows it back to, well, if it shows it back to someone else,
It would show,
it would be encrypted.
it would be encrypted, correct?
Showed back to me, ShadowCrypt looks at all the text field, like all the text rendered on the page for some I am
Fingerprint.
encrypted
Yeah.
tag. I
Exactly.
see, and decrypts it, but only for you.
Exactly. That's how it works. So naturally, that little flag, pretty easy for an application to DOS that. Just be like, okay, ignore all that stuff to prevent users from using it.
Right. But
and
even
then,
applications that, like, if the text is this big and it expands when it's encrypted to this big, and the application has something like show the first 20 characters, then ... right?
Yeah.
Then you won't be able to decrypt it, and you won't even see the first 20 characters of plain. So it might break some applications.
Yes, and ShadowCrypt definitely. The original paper went through a lot of usability studies to see how it worked on sites like Facebook, Twitter, Reddit, and they have some good results in their original paper to show usability to not degrade. Regarding like sort of if you wrote something on Facebook and a user wanting to see that, they sort of punt on key management and they sort of say users will sort of have some offline protocol to potentially share keys, so that if you were using Twitter and wanted to have your tweet only shown to your 5 close friends and not your entire follower list, maybe you'll use a particular key that you have known to share with those 5 people. But the paper in my work didn't really go into key management and how that would work.
Thanks.
Yeah.
Thanks. It's an interesting paper, interesting concept. I'm wondering, back in the early 90s, there was a whole bunch of research that went on in the concept of trusted path, and even earlier than that, but in particular in the early 90s, there was a whole bunch of publications around trusted path in graphical user interfaces. And I'm guessing you haven't read that literature. It's not online, and a lot of people believe if it's not in Google, it doesn't exist, which is unfortunate in our academic world. But I wonder whether it might be worth going back and looking at lessons learned from 30 years ago, because we were asking the same questions 30 years ago in the context of Sun Windows and X Windows and things like that.
100%, totally agree. And I think that what I'm trying to do here is just sort of provide some insights from what I got from doing this attack and combine that with insights that were from 30 years ago, and hopefully we can have a solution.
More questions? I have a small question. How did you ask the users, what was the question you asked to the users? Did you tell them, can you tell if something is weird? Or did you tell them, do you think ShadowCrypt is working? How do you?
Yeah, I can get the exact wording. It is on that link.
Yeah.
I believe the wording was along the lines of like, was ShadowCrypt working properly?
Was ShadowCrypt working properly? You have a question?
I'm curious about your second takeaway, since it was kind of glossed over a little bit. How did you come to this conclusion?
Basically the fact that the primary way for a user to think ShadowCrypt was working was just seeing that lock icon and seeing that initial border color. But that's very passive way. There was no way where ShadowCrypt was actually being able to alert the user like, oh, something is currently on top of the secure input node. It was just assuming if you see this, the user should trust that it's secure. And so those kind of passive indicators are going to be really hard. Users will just assume things are working. And so it'd be much better if the system were able to actively detect this and bring it to the user's attention that something's wrong.
We're thanking the speaker again. And
great.
next one. So next, Matthew Smith from the University of Oxford will be presenting the paper Undermining Privacy in the Aircraft Communications Addressing and Reporting System, ACARS.
Hello, I'm Matt Smith from the University of Oxford, and I'm going to present to you a measurement study that we carried out recently on the Aircraft Communications Addressing and Reporting System, also known as ACARS. This is a bit of collaborative work with Daniel Moser from ETH Zurich, Vincent Lenders from ArmorSwiss, and Martin Strohmeyer and Ivan Martinovic from the University of Oxford. So just to kick off and put this into context, this is kind of a chart of the different data links that are used in aviation. And so in recent years, we've seen quite a bit of research on various security and privacy in various surveillance systems. But there's a whole separate section of data links, general purpose data links, such as ACARs, that we haven't really looked at. And that's kind of what we're going to be looking at today. So to explain what ACARs is, it's kind of like text messaging for aircraft. It allows aircraft and ground stations to communicate via a text-based data link, and originally it was used for clocking crew in and out of their shifts. The uses now are many more than this. It's hugely wide range. You might not be able to see on the right-hand side here. This is a message from EasyJet base up to an EasyJet aircraft, and it says that England have won on penalties, and if you follow football at all, you might know how much of a surprise that is. But that's the kind of thing that they use it for now, to keep, say, passengers and crew updated on various things. And so it's served over high frequency, very high frequency in SATCOM subcarriers, and it sees really extensive usage by commercial, government, military, and business aircraft. Now at this point, I should say that this data link has no security as standard. There are some standardized solutions, but they're not rolled out with the data link itself, and we haven't really observed these standardized solutions being used in practice. So I should, at this point, cover our threat model and what we consider to be a threat here. So this has changed with the advent of software-defined radios, or SDRs, and if we look to the right of the slide, we see that there's two example SDRs here, a very cheap one that allows you to collect ACARs. This is just called the RTL SDR, costs about $10. On the bottom right, we have the HackRF, which is a bit more of an advanced bit of hardware that allows you to transmit as well. But generally speaking, we consider a passive attacker who uses this kind of hardware. They just collect messages, they store them for later use, and possibly act on them. No real kind of requirement of skill to do this. And so we use this idea to basically collect a whole load of data and see what this kind of attacker could do. So we carried out, using SDRs and commodity antenna, different collections, and no individual setup cost more than a couple of €100. Over the course of 16 months, intermittently, we collected over 2 million messages, we also carried out a survey of around 40 industry professionals to establish some ground truth opinions on ACARs to see how they felt about privacy and safety on there. We cross-referenced this with some third-party data sources, including some major flight trackers you'll see along the bottom. And at this point, I'm just going to point out one of the big benefits of using SATCOM ACARs is that you can see things that are outside your VHF radio horizon, and that's a really big win for a potential attacker. So in order to reason on what we actually mean by privacy, we first of all need to kind of organize the aircraft into different privacy-related categories. And so we do this into business, military, and government aircraft. Now, each aircraft usually has a primary purpose. They might be used for some other things sometimes, but we bin them into one category. And we do this based on 3 different criteria. So the first criteria is the registrant or the owner. So this is quite easy to check. It's just a case of looking at the public registers for these things. We also use the ICAO range. Now, the ICAO address is basically an IP address for an aircraft transponder, and ranges of this are assigned to particular countries and to particular, say, militaries. And we also leverage the plane spotting community, which is very active, and they maintain a number of really valuable data resources that have a whole range of information about different aircraft on there. At this point, I will say we don't consider commercial aircraft in this work. They have a really variable set of privacy objectives based on which airline that they're part of, so we don't look at those further. To give you a bit of an idea of what we mean by each category, so a business aircraft could be something like an Embraer Legacy. This is just generally used for moving business people or high-profile people around to meetings and so on. Military aircraft, we're kind of talking more like, say, Boeing C-17, a big transport and logistics aircraft for moving troops and equipment around, and government aircraft, which can be used for transporting politicians, state officials to, say, trade delegations or something like that. So at this point, let's define what we mean by privacy in aviation. So flight trackers, such as Flight Radar, are a public source of air traffic control data. Ultimately, this comes from the aircraft, but they receive it from many different places, and then they pass it on to the public through their website. Now, some private aircraft owners don't want this information to be public, and so they make an effort and they make a request to block this information from being public. And usually the flight trackers actually comply in doing this. However, it does mean that the only thing that happens here is this information isn't provided to the public. It is still collected, obviously. And we kind of say that because they go to an effort of actually requesting this block, asking for a block actually demonstrates a desire for privacy by the owner. And so what does this look like in practice? Well, if we take flight radar, this is an example unblocked aircraft. It contains a whole load of information on there, where it's flying from and to, the information about, say, the registration and the transponder code. But if we look at a blocked aircraft, actually you don't really see anything at all there, nothing really of use apart from the altitude. And again, you can't see the registration or transponder code. So there is a fair loss of information when they block it. And so to map this to ACARS now, basically we want to assess whether an aircraft using ACARS has some sort of desire for privacy. And the way that we do this is by checking whether these aircraft have a block on a flight tracker. And we class an aircraft as blocked if it has one of these blocks on either Flight Radar 24, Flight Aware, or the FAA bar. And if we just look to the right here, we see that from our data set of aircraft using ACARS, over 90% of business and military aircraft have a block in place, and over 60% of government aircraft have a block in place. And so for the rest of the talk, I'm going to demonstrate why, if you want privacy, using ACARS is actually quite a bad idea. So there are three main message groups that leak data on ACARS. They are positional reports, the use of information services, and flight plans. There is another kind of side bit to this to do with some weak crypto, if you can call it that, which is primarily protects positional reporting. We have an entirely separate financial crypto paper on that last year, but the key points I want to make from this are that it's a monoalphabetic substitution cipher with 9 static keys across all aircraft, and it's primarily used by business aircraft. So if you want to read more about that, do go and check out our paper. So first up, we have position reports. Basically, these can be either text-based or in a system called ADS-C, but they're super easy to spot because ultimately it's just a case of getting a kind of nice regex going to look for coordinates or the ADS-C header. Some of them are encrypted with this weak cipher, if you will, and if you look to the diagram on the right there, we've plotted all the positional reports we saw over ACARS. All the black crosses are encrypted position reports, so you can see actually a fair chunk of these are encrypted. And the problem here is that basically, regardless of whether you have a flight tracker block in place, quite a few aircraft are still sending these position reports on ACARS, and so still transmitting another stream of location data. And we saw that 52 or almost 53% of blocked business aircraft send at least one position report, so kind of undo their effort to block themselves elsewhere. Information services is a bit of a funny one and not immediately obvious why this is bad, but basically we have the Automated Terminal Information Service, or ATIS, and this just tells you information about the aerodrome, so which runways you're using and so on. But you request this ahead of time for your destination airport and your backup airport. You don't really request this for random airports. Similarly, for meteorological data, for the METAR messages, this gives you weather information at or around different aerodromes. Again, you request this for areas you're going to fly to. So with a combination of these, if we just take a look at the messages, you can quite easily pick out airport codes and figure out roughly where these aircraft are flying to and from. And we actually saw, this one's used a little bit less, but 15 to 20% of blocked aircraft across each category use these services and so reveal the route that they're going on. The real killer one, however, is flight plans. So flight plans give you obviously a very detailed set of information about where the aircraft is going, and this can be waypoints, nav aids, airports, a whole lot of stuff. And the reason why it goes over ACARS is for two reasons. One is that you can, say, change it in flight possibly if you need to, but the other one is it saves the pilots actually having sometimes to type it in and take it off paper. So there is a convenience aspect to it. And as I mentioned, it's often sent ahead of time, and so usually this means that we see it on SATCOM. Now, the real kicker of it being seen on SATCOM is that you can pretty much observe it from wherever you are in the world. You don't necessarily have to be near the aircraft to see these messages. Obviously, this allows you to discover the route of a blocked aircraft ahead of time. this was a real problem for military aircraft. We saw 347, or just under 70% of blocked military aircraft transmitting flight plans. And so we plotted them, and here they are. You can see a whole load of plots from the US to Europe and all around Europe. I'll come back to this one, though, in a little bit. So I just want to it's all very well talking about this in an abstract sense, but I want to give you some concrete examples of exactly how this can cause problems. So I've got two case studies. So the first one is a military aircraft. Now, this military aircraft was blocked on all flight trackers, so if you try and search for it on, say, Flyradar, it's not there, it hasn't flown. This aircraft sent 513 ACARS messages over 3 months, all of them on SATCOM. And 16 of those were flight plans and 32 were ATIS messages. So as I mentioned, we can get a lot of data from that. Now, obviously, this contained initial flight plans as well as updates and routes. And so if you look to the diagram just on the left, you can see we plotted one of these, huge amount of detail. We could see that it was flying from southern Spain up to Ramstein Air Base in Germany. And we could see a very detailed flight plan of how it was getting there. Obviously, otherwise, we wouldn't have been able to see that information at all. This is quite a kind of small canned example, but sometimes sending even fewer messages can reveal even more. So we saw a US diplomatic fleet aircraft inconsistently using ACARS despite being blocked from most flight trackers. And this one was usually SATCOM based, occasionally used VHF ACARS. But in one case, we collected 5 messages over the course of an hour, and we reconstructed quite a nice diagram of what it did. And so this is the diagram, and so I'm going to dive into just the bottom corner of it first. So we see that, first of all, we get SATCOM contact just before 5 a.m. from Saudi Arabia, and we get a flight plan. And this is how we plot the blue line from start to finish. A little bit later on, just before 6 a.m., sorry, that's my box there. So just before 6 a.m., we get a load sheet and passenger information sheet in which there are some code words on. We don't know what they are. We've seen them on other messages, but they only, as far as we're aware, they're only sent by the US diplomatic fleet aircraft. And then we don't really actually hear anything from it again. We don't really see any surveillance messages from it, apart from 25 to 12 in the morning. It briefly turns on one of its transponder to send out some surveillance messages, and then turns it off 25 minutes later, at which point normally we would have lost track of it and we wouldn't be able to see it. However, because of our ACARS messages, we could see that it was then flying onto Shannon. What I've not plotted here is that there was an entirely separate set of messages that showed that later on that day it then flew back to the US and gave the exact flight plan for that as well. And so that's just to highlight the ADS-B bit there. So obviously this is not great. So how do we fix it? Well, as I've mentioned, there are actually some solutions out there, right? There is a standardized cryptography suite for ACARS. However, no one really uses it. The only example of crypto, if you can call it that is used is that cipher that I mentioned earlier. So they either use that, maybe use a non-aviation specific crypto system, but definitely not rolling your own. That's not gone well so far. The other option, the extreme option, is just to switch ACARS off for sensitive flights. Now, this will stop you leaking data, but the pilots won't enjoy it. They actually use it quite a lot for their day-to-day jobs. So the in-between option might be to firewall this at the service provider level and stop the automated requests for, say, position going up to the aircraft. So that's one way to get around it. Obviously, we should also consider the non-technical approach here. I've not covered the survey too much in this talk, but we did find that basically some professionals in the industry are aware of the problems with this, but it's not a wide enough set because it's still used in this way. And so clearly there needs to be some policy to define whether sensitive flights should be using ACARS at all, or if they do, in which way. And there is a question to do with charter business jets of, well, if you are paying to fly on a business jet, do you know that your data in your location is actually potentially being leaked? So just to wrap up, ACARS is a legacy system used for way, way more things than it was originally intended, which have caused a whole range of problems down the line for location privacy. Many observed military, business, and government aircraft have made a concerted effort to try and hide from your conventional sources of flight tracking. But actually, the lack of by default security and the effectively misuse of the system has undermined any other attempts at location privacy. Unfortunately, ACARS will be used in the medium term, so we need to do something about it in the meantime. So that's all from me. I'm happy to take any questions.
So I was wondering about the businesses that use the privacy settings. It seems like, you know, on FlightAware and whatnot, a lot of the large commercial flights, there is quite a bit of data available. Is that mostly sort of private charter, smaller business type things, or what's the?
Yeah, exactly. So I'm sure there's a rule somewhere. It's actually very hard to find because we've tried to find it a few times. But the kind of rule is that commercial aircraft don't make any effort to obscure their transmissions. There is an argument that this is a safety-related feature. I don't agree with that, but that's a separate discussion. Yes. So the business aircraft we talk about are specifically, say, aircraft owned by multinationals or corporations or high-profile individuals. You sometimes get, say, a charter organization that will operate 20, 30 jets, and they will use this block. But Flight Radar and FlightAware and so on have no provision, as far as I'm aware, to actually block commercial aircraft.
More questions?
You said it's a legacy system, and sometimes people don't use it. And I was wondering what do people use instead, or like, is there a more modern thing that is an alternative that's used?
Sort of. So there's two answers to this. So some airlines just choose not to use it on a cost basis. So Ryanair is quite a well-known example. They choose not to. Having spoken to Ryanair pilots, apparently it's actually a bit annoying to not use it. However, it's kind of a convenience thing, right? People have got used to it, and so now kind of all expect to use it. In terms of other options, well, the industry is aware that this is quite old, the data rate is very low, the message size is really small, and so they do want to move on from it, but as with all aviation systems, it takes a long time. So we're in the process now of designing the next set of data links. They won't be deployed for at least another 15 years. So ACARS in some form will be used in the meantime, and as long as we use ACARS as it currently is, there is unlikely to be any sort of transport level security on there.
Have you reported this to RAF or NATO or anyone like that, and if so, what's the reaction?
So it's a bit of a funny one. So I have spoken to people, so we haven't spoken specifically to militaries and so on. This is more of a case of often finding the right person. We have tried with all the previous projects to report the findings, but you often, unless you know exactly the right person, you won't really get very far. In some other work, we have reported it to a commercial operator, but no, to answer your question about NATO and so on, we haven't. However, the people who operate the network are aware that it's misused. They do try to tell people not to use it in this way, but unfortunately, it's a bit of a force of nature. That answers your question. So.
Just a suggestion that you might talk to your funding agency if this is being funded from the government, because they may have the ability to make inside government contacts in a way that you can't.
So it's something that we are, as time goes on, we're getting better, kind of getting to the right people, and you're exactly right.
Could you just touch briefly on the governance landscape internationally? Like, who is the people making these standards?
Sure. It's a kind of big multi-level setup. So at the top you have ICAO, and they do high-level regulations. So they will say, okay, well, you know, aircraft must meet these safety standards and so on. Then it's devolved almost continentally, which then it gets to be the more specific kind of regulations. And so in terms of this, an ACARS, the level at which you would have to regulate to make changes would be probably at the kind of continental level, because the international governance is too high level to do it directly in a fast way, is probably the best way to put it.
Last question there?
Sorry. Could you explain quickly the historical reasons why they came to use this absurd crypto system instead of what was available?
The cipher that I mentioned in the talk. That's an interesting question. So as far as we're aware, and we only have partial information on this because this is not a standardized cipher. This is offered by a specific company on a specific set of avionics hardware. It seems like there was a business requirement. People became aware that they were sending location data over ACARS and they didn't want to. And there's been this big kind of push-pull, and no one really wants to pay for the standardized solution. It's an added extra, you have to pay more for it. So it seems like this company came up with this system as like an in-between, right? Something they could just offer as a bit of a add-on to their avionics package. Now, we're not 100% sure on that. We have asked, we haven't got an answer. Yeah, we have got details as well, and we did do responsible disclosure with that. The details are in the FC paper. It's too long a story to tell now, unfortunately. But I can tell you offline as well.
So with that, let's
Thank you.
All right, so we're coming to the last talk of PETS 2018. And it will be given by Lucy Simcoe from the University of Washington. So after attacking graph topologies and shadow crypt in first, it's going to be authorship attribution programs, and she will present the paper looking at recognizing and imitating programmer styles.
Thanks. So hi, I'm Lucy, and I'm going to talk about source code attribution. So let's say, sorry? Is that better? Yes. Okay, thanks. So let's say you have some code and you want to know who the author is. So you might compare the coding style of the code you have against a set of code where you do know the author. And you say that the unknown code is written by the person whose coding style most matches it. And that's source code attribution. Previous research has achieved high accuracy on this kind of problem. In 2015, Calscom Ismail published a classifier that achieved much higher accuracy over larger groups of authors than anything before, 98% over 250 programmers. And for their dataset, they use Google CodeJam, which is an annual programming competition that's also used by PriorWorks. And we use this as well. So there's this powerful source code classifier. My question is, what if you don't want your code to be attributed to you? For example, what if you're developing a popular cryptocurrency and you don't want people to know who you are? And more generally, you might develop software outside your day job that you don't really want to be connected back to you for privacy reasons. So you might want to write your code that tricks a source code classifier. Or what if you're a developer in a country with censorship? Someone making an anti-censorship tool might want to preserve their privacy by writing code that doesn't look like they wrote it, by substantially changing their programming style, among other defenses. And on the flip side, someone might want to intentionally frame you by writing code that looks like you wrote it, creating a forgery of your style. So the main question here is it possible to fool source code attribution classifiers? And the answer, of course, is yes, we can. And it's important to note that we can ask this question because strong attribution classifiers like Calscom Islam's now exist. This is a nuke attack, so the classifier wasn't built with this in mind, and defending against this kind of attack was not part of their original design goal. So in order to learn about how we might fool an attribution classifier and why it might be possible, we ran a lab study in which we asked a number of programmers to try to modify code to imitate a certain author. So now I'll define source code attribution a little bit more formally so that I can talk about what it looks like to evade source code attribution. So back to this simple diagram of source code attribution. I've told you about the state-of-the-art classifier, so let's put a classifier into the diagram. The classifier is a black box that the code goes into, and out of all the possible authors, the classifier picks an author, in this case, author C. I'm going to use P sub C to represent some program or code written by author C, which goes into the classifier. And instead of showing the set of possible authors as a pile of stick figures, I'll use this notation at the bottom to show the authors that the classifier is trained on. Let's say it's 5 authors called A through E. So this is what source code attribution looks like. You take some code, for example, by author C, you put it into a classifier that's trained on some set of authors, which includes C, and the classifier outputs the name of the author whose style best fits the input code. And in this case, it's correct. So now that we've defined what normal attribution looks like, we can get back to the main question about fooling these classifiers. So what would you do if you wanted to trick the classifier? I'm going to call the person doing the tricking the adversary because they're acting adversarially to the classifier, not because they're necessarily malicious. The first thing that the adversary would do is look at code from the author that they don't want the classifier to recognize, and learn as much as they can about how that person programs. This is the original author of the code. In some cases, this might mean looking over their own code to learn about their own stylistic choices. This isn't what we tested, but it's a reasonable situation if you're trying to modify your own style for privacy. And if, like the participants in our study, you might also look at code from a target author if you're trying to make the classifier guess that some code is written by someone specific. So then they'll take some code and modify it to imitate the target author's style. And I'm going to call this forgery because the adversary is forging the target author's style. And there's another possibility. What happens if the adversary succeeds in changing the classification away from the original author, but the classifier attributes it to some third party other than the original author and the target author? For the purposes of this research, this is a semi-successful forgery because they hid the real author's identity, but they weren't able to actually create a forgery of the target author. And I'm going to call this masking because the adversary is masking the original author's identity. There are reasons that someone might want to actually intentionally create a mask, meaning that they don't have a target author in mind. But in this research, we focused on forgeries. So this is where the adversary fits in. You start out with P sub C, again, just some code by C. And then some adversary comes along and they manipulate the code and they create P sub C prime. They put it into the same classifier and the classifier makes a guess. And with forgery, the adversary's goal is to imitate a specific author. So here, if their goal was to imitate author A, then they would be correct and the forgery would have succeeded. And I want to emphasize again that the classifier is a black box for a reason here. We're not assuming that the adversary or any of the authors know anything about how the classifier works. If the adversary did know how it worked, they could tailor their attack to the specific classifier. So now I'll talk a little bit more about what we actually asked our participants to do. So broadly in our study, we asked C programmers to act as the adversary and create forgeries. All the code in our dataset came from prior years of Google Code Jam, which is the same programming competition that prior work has used. We used C code from Google Code Jam, and unlike prior work, we linted the code to remove a lot of the typographical differences. We did this because we wanted to force the people making forgeries, our participants, to focus on less trivial differences than, for example, bracket placement. And in the real world, production code might not have these differences if a company has really strict style guidelines. So there are about 4,000 authors total with C files, with about 2 files each on average. We took the code from the five authors with the most files, who I'm going to call A through E, and we used these authors as input to our classifiers, and also as the original and target authors for the forgeries. And we used these authors, the ones with the most code, because we wanted to give the classifier as much data as possible to improve classifier accuracy. And we tested participants' forgeries against 3 versions of the state-of-the-art classifier, the one by Kaliskin Islam et al. The versions differed by the number of authors in their training set. And the first version was C5, trained on 5 authors, A through E, who are the authors with the most code. And this classifier has 100% accuracy. The next classifier is C20, trained again on A through E plus 15 random authors from Google Code Gem, and the precision and recall were in the high 80s. And finally, the last classifier is C50, trained on A through E plus 45 random authors, and precision and recall in the mid to low 80s. So we took our 28 participants and we asked them to act like the adversaries. First, we gave them sample code from 2 authors from the set of A through E, who I'm going to call X and Y, and then they modified code by one of the authors, let's say X, to look like the other author wrote it. And finally, we actually let them test the forgeries against oracles to see if they were able to fool the classifiers. We didn't tell them about the oracles until they had a forgery attempt in hand, so they didn't create their first attempt with the oracle in mind. And the only information they gained was what the classification decision was. They didn't know anything about how the classifier worked or why their forgery succeeded or failed. This isn't necessarily something that would exist for all adversaries, but in designing our study, we thought this might motivate our participants to continue trying to fool the classifiers. And in practice, we think that real adversaries would be much more motivated than our participants. And a real adversary could also very easily use the same classifier that we did, since it's open source, and depending on their original and target authors, they might also have access to code to train on. So in this example, this forgery PX prime is fooling C20 and C50, since those classifiers are outputting Y instead of X, and it's not fooling C5. So in this example, the participant would see this and they would continue to change PX prime, or they'd choose to end the study. So now into the results. I'm going to first talk about a conservative estimate of adversarial success. And this is conservative because our participants were not experts in forgery creation. So this table shows how often participants were able to trick the actual classifiers. The columns are the classifiers, from left to right, C5, C20, and C50. And these numbers are from the final attempts the participants made, that is, after they had access to the Oracle classifiers. The first forgery attempts are slightly lower, but they're similar. The rows are the types of attack, forgery or masking. Remember that the participant's goal was forgery of a specific author, but even though we asked them to make forgeries, sometimes the classifiers output answers that were not the target author and also not the original author. And for the purposes of this chart, the masks include all forgeries as well. So the 66% here means that 66% of forgeries were successful against C5. 66% of the forgeries fooled the classifier into thinking the target author was the author instead of the actual original author. And down here, for C50, 86% of the forgeries resulted in some misclassification, meaning that they at least matched the original author's identity. So on non-adversarial data, remember, C50 had accuracy in the mid-80s. So this is a huge drop in accuracy on adversarial data to about 13%. And the lesson here broadly is that non-experts can successfully attack a state-of-the-art classifier. And this suggests that other classifiers might be vulnerable to the same type of attack. Okay, so we've shown that forgery is definitely possible, even when the adversary is not an expert and when the classifier performs really well on non-adversarial data. Now we're going to look at how these forgeries were created so we can start to talk about how to make a classifier that's more difficult to fool. One overarching lesson, before we even look at the modifications, is that forgers didn't know how the classifier worked or what it was looking for. So they weren't crafting forgeries specifically to fool that classifier. This means that forgeries in the wild might contain the same types of modifications. So moving on to the modifications, it's easier to actually just show an example. Here are two snippets of code, both by author C. They haven't been modified by anyone, they're just straight up author C. And they're also not functionally equivalent, so don't try to compare the functionality. And I've removed a little bit of the setup code. So as you look at these, try to think about what might be indicative of this author's programming style, or what you'd expect to see in other programs by this author. This is exactly what we asked our participants to do, except they had more code and a lot more time. So I'm going to highlight a couple things that people noticed. You may notice other things in there. At the very top in yellow, there's these funky pound defines. They use rep for a for loop. They just pound define it as something called rep. In the green, they have some variable names that are always the same, I, J, K, L, M, N, and then size and count. And then also some as well that aren't. When they read in data, they use scanf and nothing else. And then for loops, they typically use the rep that they pound defined at the top. But for their main loop in their main function, it's always while size minus minus. So these are a couple of things that participants noticed. And these are the same things that I just talked about, the stylistic elements, split into two groups. On the left, there's information structure, which just means variable names, syntactic decisions, macros like the reps and API calls, and control flow, which here just means loop type. So now I'll show you how people used these and a couple other modifications to create forgeries. I'll come back to this chart in particular and add a couple more after an example. So here's an example. On the left, I have some code by author A, which is not a forgery. This is just by author A, and all the classifiers correctly identify it as author A. I'm going to show you how someone created a forgery that maintains the functionality of author A's original code. So I just put the same code on the right. This is the code that will transform into a forgery. Right now, it's exactly the same. The code on the left will remain the original code, and the code on the right will transform into a forgery of author C. So first, we'll just copy in the distinctive pound defines. Then we'll change some variable names, CC and CA to size and count, and also change them down there so the code still works. Then change the input from CIN. We saw that author C liked scanf, so we'll change all the CINs to scanf. And then also thinking about loop type, we saw that they liked to use rep and size minus minus, so we changed those in the same way. And then the forger also moved that scanf up a little bit because we linted imperfectly. The linter didn't realize that rep was a for loop, so that's an example of a typographic difference. So this was a successful forgery. It fooled all the classifiers. And it's really interesting because the forger didn't need to understand the code to make these modifications. They could just make modifications, which means that they could make modifications to complex code that they don't understand. So here's the same chart that I showed you before. We did discuss a third group of modifications, typographic, which occurred because the linting wasn't perfect, like we saw. But for the sake of time, I'm not going to really talk about these because they're generally pretty easily to make with the linter, and not all authors will even have typographic differences. So here are a couple more modifications, including libraries that are imported, location where variable are declared, if statements, control flow keywords, loop logic. And all of these modifications, like the ones we saw in the forgeries, you only have to have a really local understanding of the code to make these. So I'm going to call them local changes. If you have a more comprehensive understanding of the code or the engineering decisions that went into it, you can make more complex changes, which we're calling algorithmic modifications. To make these, you need to know more about what the code is accomplishing and why the programmer made these. So information structure algorithmic modifications would be, for example, changing variable types or data structures or anything that intentionally affects memory usage. And it turns out that even though local infrastructure changes were really common, especially variable names and adding in libraries, no one actually made the more complicated changes, even though they came up in notes as differences they noticed between authors. We did actually see some algorithmic code flow modifications, like refactoring functions or inlining API calls, or making big changes to if statement logic. But for both categories, local changes were still a lot more common. There were lots of changes to loop type, like we saw, as well as loop logic, like making the counter increment instead of decrement. People found clever ways to add or remove control flow keywords like go to, break, and assert, without really changing much of the surrounding logic. So there are two main takeaways from our analysis of the modification that created these really successful forgeries. One takeaway is that local modifications are very common, and the forger only has to understand a little bit about what's going on in the code. And another takeaway is that people often copied code directly from the target author's training set. In these forgeries, they were just copying single lines like we saw with the reps, but in the pilots we saw some people copy entire functions and just use them as dead code. So it might be useful for a future classifier to look at code reachability and whether all the variables are actually used and analyze those sections of code differently. So in summary, we conducted a lab study with C programmers who produced forgeries, and we tested these against the state-of-the-art source code classifier. And the high-level summary is that our relatively unsophisticated adversaries were able to fool a state-of-the-art classifier, and the forgers were successful, even though the forgers only made changes that didn't require them to really understand what the code was doing. Thank you, and I'd be happy to
Questions? All right, 3 questions. 4, wow.
Okay. So can I start?
Okay, go ahead.
Okay. So one question I have, if you want to automatize all of this,
Sorry, I can't
if you want to automatize, so not use any human, but to do it on a large scale.
to automate the modifications?
Yeah.
I think that's definitely possible. I think it's outside of my technical ability, but I think it would be really interesting. And I think there are also more difficult modifications that would be harder. Like changing variable names, you could very easily automate that. But changing other things would require a deeper understanding of the code. Does that answer your question?
Yeah, and my second question was, if a human would look at the code, you think it might be able to detect the forgery?
I'm sorry, I really can't hear you.
So if a human would look at the modified code, you think he could detect the forgery even if the classifier could not? So if you have an expert programmer which is looking at the modifications that the people have done, do you think he might be able to distinguish between the real code and the modified ones?
Whether humans can see the difference?
Yeah, so my use case would be like for attribution of malware. Suppose that I'm a country and I want to appear that another country made the malware. I wonder if even expert human would not be able to tell the difference between modified code and the original one.
That's a great question, thank you. I'm sorry it took me a while to understand it. It was kind of hard to hear. I didn't have time to talk about it in this talk, but we ran a separate study where we actually asked humans to be analysts, basically. We gave them these forgeries and asked them to say, before we told them that they were forgeries, we said, is this code by X or Y? And they did not do very well on the forgeries. But I think if someone is aware of the forgeries, we saw this by the analysts, that they did pretty well at finding the forgeries. So I do think it's possible for a human analyst to tell forgeries, especially if you give them specific training, if they have more information about the authors. So I do think so.
Thank you very much.
Thank you.
Okay. So that was a great talk and a great paper. I was wondering if you could, if you think there's something in your findings that then people could use to build a classifier that's specifically to look for forgery. Maybe not even that maybe it does worse in the general case, but it specifically targets forgeries.
That's a really interesting question. I think there are several things that you could look for. I think you could look for, so we saw a lot of local modifications. So kind of, if you look for code where like maybe the very local style, the variable names appear like one author, but then you can develop like a higher level understanding of the programming decisions, like maybe where they're declaring the variables, where they're using their variables, how they're treating the data. Like if those don't consistently look like the same author, I think that would indicate a forgery. Thanks.
So, do you think if you were not trying to forge other people, like to change other people's code, but that you were trying to change your code, which is probably a much more realistic thing that people do in the wild, do you think it would be easier or harder? And like what, this conclusion?
That's a great question. I don't know. I think it would be easier because you know what the code's doing. And I think it might be harder because you might have a harder time thinking about other ways to solve the problem. Like how do you solve a problem in a way differently than you normally solve the problem? I think that would be difficult.
Thanks for the talk.
Thank you.
In light of the sort of, you did this nice analysis about the types of changes people made locally and so on. Did you look at, in the classifier, like how that affected the different features in light of what sort of Edwin's question? It seems like just looking at this that it would, that you'd see much heavier changes to the layout and lexical features, whereas the abstract syntax trees, except for the cases where people were making the more algorithmic changes, but maybe not all of those, you'd see this interesting disparity. Did you do any feature analysis like that?
We did, yeah. I didn't have time to talk about it, I'm sorry.
Cool, I know you did a lot.
Actually, I was expecting that as well. I was expecting to see that people were mainly changing the lower level features, and we actually didn't. We saw that there were a variety of features changed. We did an analysis of comparing original and forgeries, and I believe there were like 2 features that were constant. And there was no good reason that they were constant in all files. It was just that they hadn't been forged by those particular forgers. So I don't think there are unforgeable features. And yes, the answer is yes, that people changed a variety of features, even though, yeah, sorry.
Interesting. Thank you.
So the same kind of stuff has been done in natural language, right? Where essentially if you try to change your writing style or try to change someone else's writing style or imitate someone else, you can trick the classifier. But I think some of Rachel's work has shown there that then the confidence levels of the classifier aren't as high, so these samples are actually pretty easy to detect. Did you note this when you were looking at your results?
We did not, but I think that'd be really interesting to look at and could be another way of detecting when something's a forgery. That's an excellent idea.
Last question?
Okay, I have an ethical question. So it seems that what we're doing here is proposing a system that uses the code of many, many developers that are in open source and free software or whatever projects to surveil on them and their colleagues. And I'm wondering, have you thought about when is this acceptable and not acceptable? And what are the chances, for example, that employers would start taking this to check on the productivity of their coders, which they already do? And I've also heard that governments will use these kind of techniques to conceal the fact that they're actually doing much more intrusive surveillance. So they'll say, we found attribution using these methods, when in reality they've been doing much more intrusive surveillance of coders. So I'm wondering if you have confronted these ethical questions and what you think about them.
Personally, I have opinions about these. I think these have been used in practice. I'm not an expert on ethics. There is an example of an Iranian developer who was sentenced to death for writing photo sharing software, which was used for explicit material. So that's an example of where you might want to evade it, and I think, personally think that would be ethical, but I think it really depends on the context. Maybe you're a company and you want to be sure that the people you are paying are actually doing the work. I think there's a variety of situations, and you really have to look at the specific situation. And it really depends on who it is.
Okay. Thank you very much.
Okay, hi everybody, and welcome to the PETS 2018 Rump Session, Lightning Talk session, where we have a packed group of people who are going to tell us about all sorts of things with up to 5 minutes each, and I'm going to keep talking until Joel has his slides up.
So who's in charge of putting it on the screen?
Who's in charge of putting it on the screen is the question. Is it?
Excellent.
Yes? So close. And the goal of this is that all of these interesting people should be around tonight and tomorrow and the next day, hopefully, for you to talk to about whatever their interesting talks are. And first up is Joel, and after that is Ian.
All right. Hello, everyone. So if you remember, Erwin gave a talk about... I don't need the microphone. I'll just shout. There is one, if you wish to, or you don't. Thank you. So, if you remember, Erwin gave a great talk about looking for privacy violations in children's apps. If you recall, we had an automator exerciser monkey, and it was running on a cluster of phones collecting a lot of reports about transmissions. In this talk, I'm going to talk a bit about the static analysis that went into, because it turned out a lot of the ad libraries actually use some kind of obfuscation. So, our first example, here we have com.disney.gossipgirl story games. And it's a Disney game. You can see it's sending a packet to Chartboost. And it's courteously recognizing that the limit ad tracking flag is set to true. Very nice. One presumes that this identity blob, which is clearly unreadable, is just simply not processed when it's set to true. If it's set to false, then maybe the person on the other end is able to unbasic for it and see that there's the Android ID, a non-resettable identifier except through a factory reset, and the advertising ID. And when you look at this a lot, you begin to notice and just see the EYJ as just the beginning of a JSON object in base64, which brings us to our next example here. This app had the clever trick of having uncomprehensible base64 when you decrypt it or decode it, and then you notice the EYJ here at the end. Now this is my fault. I didn't realize that there was a little endian and big endian base64, so I added reversing this and was able to see that, in fact, it was sending things such as the phone's IMEI. All right, our next example. Here we have a game from Mattel, and they are sending the IMEI of a phone, and they're sending the Android ID as well, And they also have it repeated in this big blob here, where it appears first at the top as the IMEI and then the Android ID. And then the question is, what are all of these other values that are being listed on this field? What are they all corresponding to? So we did a little investigation. We see that clearly we have the IMEI and the Android ID. And the next step was to see that, well, it's the MD5 of the IMEI twice for some reason, the SHA-1 of the IMEI twice for some reason, and the SHA-256 of the IMEI twice again for some reason. And okay, you know, these are clearly computable on the server end, but we'll just run it on the phone for some reason. And the Android ID, it was the same sort of trick, except it wasn't coming in pairs. Right here, we see that it's happening twice, it's being sent twice. In this case, we weren't seeing this behavior. So we thought about it for a while, and what we came up with was a realization that it was actually the MD5 of the uppercase of the hexadecimal representation of the Android ID. And what they're doing here is they're still calling the toUpper function, but because, of course, numbers don't have upper cases, it ends up being the exact same value being sent. And well, I guess this will be bothering us throughout the entire rump session. So let's close that. And now it's completely frozen. Great. And this concludes my talk. Is it actually busted? Yeah. Okay. Carmela, what's that? I do have a lot more, but it's frozen. It's showing malware virus instead of. Okay, thank you, Joel. Ian is up next.
All right, luckily I don't have slides. So
And Sajin is up after that, and hopefully Carmela. Okay.
But I'm like 30 seconds. I'll need the mic. Okay. I know Joel had like way other funny stuff, so maybe we'll get to see that over drinks later. Okay. Hi, I'm Ian, and I'm an academic. It's been one day since my last paper. So I just wanted to say that we at CRISP at the University of Waterloo, we have lots of people here. You might have seen our spiffy lanyards. So you can go talk to all the Waterloo people here. I just wanted to drop that if you're looking for a postdoc position, if you're looking for a faculty position, we're hiring. We'll be hiring in security this year for sure, in faculty positions, and we're definitely looking for a kind of pets-oriented postdoc. So if you're interested in any of that, come see me, and maybe we can see the rest of Joel's slides. Okay, thanks.
Thank you, Ian. Speaking of broader Waterloo people, we have second Joel coming up soon, and after that, Sajin.
All right, thank you, Serge. There. Let's hope it just works. When what's the magic keystroke? You want the arrow? Just drag the window over onto the next screen. And to make it full?
Upper.
Go up to the view as right, it just works. I really need to Where's the cursor?
Let's see how many people fit on stage.
Yeah.
You're both trying to use a laptop. This one is says that this is working on updates. How is the research on the laptop? 100% completed.
Like you send some Bitcoin to our onion address, and you have your laptop back. Why are you doing this in the browser?
All of the rump session people who can do their own laptop should consider doing so.
Okay. So the next thing that people were doing, they were using encryption to actually send their data. Here what we noticed was that they had an encryption key, and it's just written nicely in the clear text right at the file right before they called the AES and CBC mode. The interesting thing about using CBC mode with a fixed IV is that it doesn't actually add a lot of value. And what's amazing is they actually have a number here, which suggests that they actually deliberately generated an IV at some point, and that's what they came up with, and they decided, okay, perfect, that'll work. The next one was iron source. Again, fixed key. They had to pass it into a function, so I had to go one step out to find where it was getting passed into. The interesting thing that they call it decoding instead of decrypting and encrypting. Their IV is just 0 being flushed into a buffer, but they do something else that's interesting. They pass in the key into this getBytes function to get a byte array of the values, and of course the actual key has a lot less entropy because it's just the binary of the ASCII representation of the key. This happens a lot, so I was trying to figure out why a 256-bit key wasn't working, and it turns out it was actually, or rather 128 wasn't working, it was a 256-bit, but with a lot less entropy. We focused on iron source because they sent a lawyer message at us, so that added them to the top of my attention. More on that in my talk. And as well, finally, we saw in one case, Startup, they were sending these something called locations, and when we decrypted it, or base64 decoded it, we got something that actually had a lot of shape. It looked like printable characters. It wasn't random binary data. It was also not readable. So we came to the realization that, well, if we XOR it with some string and all the dots are non-printable characters, it happens to be exactly the GPS location. Well, this doesn't prove anything, of course, a one-time pad can turn anything into anything else, but if it happens to be the one-time pad of encryption key, encryption key, encryption key, encryption key, and the name of the developer of Startup written over and over in a sort of hacker leet speak. Because of the earlier time, I'll skip to the very end and just say that they also have a Startup encryption key that they use to send incoming packets that get sent out that never actually gets used on the device. And I had to use Alfred Menezes' trick of breaking Vigenère cipher that he taught me in 4th year crypto, and it works. So the classic techniques still work to break crypto. That's done wrong. Thank you.
So Wouter will be up next. And if you are soon and don't have slides, you'll also be up next while we wait for the fine laptop to do whatever it's doing.
Hi, I'm Wouter.
Hi, Wouter.
I don't have slides. So that's awesome. So you might have heard me talk about some of the cool Tor projects that we've been doing, building a medium latency thing on top of Tor without changing Tor, and maybe even something scarier like putting some lightweight Tor thing in the browser. And some of you were here at PATS, well, not here, but were at PATS 2 years ago and know that when you put a lot of Tor things in your projects, then Ryan and Tara can come around with the Exterminator, which is not a very good thing. So I just wanted to let you know that we're also doing some cool sort of applied crypto stuff, protecting your keys on your mobile device without sort of reducing all the privacy that you worked so hard on to get. And in order to sort of convert all this crappy code that I'm writing, so all this postdoc code into nice code, we're actually looking for a software engineer. So if that is you or you have a friend who that might satisfy, come talk to me or Camilla afterwards. Thank you very much.
Thank you. And Nick is up next, and after that, we'll figure it out.
Hi, I'm Nick. I don't need slides, I'm just that cool. And I just wanted to tell you about a cool thing that went into Tor that you might have missed. We actually found a use for order preserving encryption. Yeah, I know, seriously. So, a lot of people like to do sort of cheap multi-homed onion services by just running the onion service in a few different places and letting them take turns uploading. The problem is that in our revised onion service design, we replaced an old timestamp, because timestamps are scary. Ask me later if you don't know why timestamps are scary in privacy systems, with a revision counter. But of course, if you're doing the trick of cheap multi-homing, then everybody's revision counter will get out of sync, and whoever just uploads the most revisions will win. because the directories will hold whoever has the highest revision counter. But if you do a order preserving encryption of the current time, then you can actually get something that satisfies the property of being monotonically increasing and not leaking the exact time of the device, thereby creating a fingerprint of the device. And we're doing that. There's a write-up at the end of Rend Spec v3, the current hidden service spec, in one of the appendices. And fortunately, we're not relying on it for very much, because I bet one of you will tell me that it's broken sometime in the next month or so. But thanks for listening.
Okay, Kevin is up next, and if you are doing the rump session and can do slides of your own successfully, let me know and you can be up after that.
Hello everybody, my name is Kevin. I'm a PhD student at NYU, and a lot of my work right now revolves around the usability of the Tor browser. I'm going to talk to you a little about work that I've done that's going to be coming up at CCS, and then about the next project I'm going to be doing. So if anybody would like to work on that with me, I'd be willing to talk. So recently we did a in the wild, or pseudo in the wild, collection of usability problems of the Tor browser. And the way that we did that is we created 3 surveys that individuals filled out at if certain criteria was met. And that criteria was measured using a Python script on their machines. Now, all that did was determine when they closed the browser, and they launched the survey whenever a browser was closed. So if only the Tor browser was open, they closed the Tor browser, it launched the survey asking them about their experience using the Tor browser. If we detected that they switched browsers, it would launch another survey that said, hey, why did you switch? We would really like to know what the other browser is doing that the Tor browser couldn't do for you. And then the last survey was if they didn't even bother with the Tor browser at all, it just launched a survey saying, hey, why did you use another browser instead of the Tor browser? No information was sent to us unless they explicitly filled it out in the surveys, and that's how we did our best to preserve their privacy. Now, we have a whole bunch of interesting findings from this, including what went wrong with the Tor browser. The paper is going to be published in CCS soon. One of the things that we determined here is that there are a lot of websites that simply aren't working on the Tor browser. I'm sure that's not a surprise to a lot of people who use Tor here. So the next project that we have coming up that we want to work on is creating a Tor friendliness scanner in order to scan the internet and sort of give it a Tor friendliness score for each website that we come across. For this, we need a modified version of the Tor browser that logs things that are blocked. I'm currently starting work on this project now, and if anybody's interested in working on this with me, you should talk to me as soon as I'm finished talking, as soon as the rump session is over. And any other similar Tor usability work that you would be interested in working with me on, please let me know. Thanks.
And Susan is up next, and 3 Beccas are up after that.
Hey, what happened? Oh, goddamn. So how do I? Man. Okay, here we go. Okay, so I'm here to talk about the second crypto wars, and where did the rest of them go? I'm here to talk about they're not even up. I'm here to talk about the second crypto wars, with or without slides. Mike, slides. Slides aren't coming up. 2 years ago, I testified in Congress just after James Comey. This was in the middle of the Apple crypto wars. Comey was arguing that Apple needed to build stuff to open the phone. As you probably all know, he argued that only Apple could build anything that could open the phone, and it turned out, of course, that somebody else opened the phone instead. And we don't know exactly who it was. There are various theories. Last spring, a couple of months ago, the FBI Inspector General released a report that said it turns out that the FBI didn't try as hard as it might to open the phone. That is, the case happened in December 2015, the San Bernardino terrorists. In February of 2015, the science and technology executive of the FBI got a little nervous. She'd been testifying in Congress. Comey had been testifying in Congress. They'd submitted an affidavit to the court that only Apple could open the phone. And she thought that maybe FBI wasn't trying as hard as it might. It turns out there are two different organizations within FBI to do this kind of work. The one that builds its own solutions, which hadn't been able to, and the one that contracts out. The one that contracts out had thought that if any solution appeared in court, it would have to be completely exposed and hadn't been trying to do it. Nobody had said, go ahead and do it. So it turned out that the testimony was incorrect, although they were not lying. And I want to actually give kudos to the FBI science and technology exec who pushed that, and then we know that story. Move forward a little bit. Why is the phone so important as opposed to end-to-end encryption? The phone is important for lots of reasons, including the data that you have on the phone. It's a privacy issue, but it's also a security issue. And a security issue is the issue of what you use for second-factor authentication. When your phone is missing, you know your phone is missing. And the phone is the easiest device for second-factor authentication for the broad general public. So it's a real security issue. And that's what brings me to the next thing, which is the Academy. Oh, so I forgot to mention, and I came out with a book. It's unlike the academic books I've written before. This is more for the general public, but there's lots of stuff you guys don't know in it. There are book flyers over there which give you 25% off. It's called Listening in Cybersecurity in an Insecure Age. I think it's great. Academy did a study on plain text and access to plain text, coming up with a framework of how to decide what the trade-offs are in access to plain text. This study came out this spring. It's a set of questions that legislators should look at and examine in the context of deciding whether or not to do legislation regarding end-to-end, which I don't think will happen, and access to devices, which I think could happen. Third thing I want to tell you about is during the course of the Academy study, Ray Ozzie and two others came and briefed the Academy study, claiming they had partial solutions, or directions, or whatever. We mentioned that in the study. Wired magazine picked it up and did a long piece about Ozzie. I arranged last spring a security group of the usual suspects, Blaze, Bellevin, etc., to go over Ozzie's proposal. There were a lot of problems with Ozzie's proposal, which is something I would actually call not a proposal but an idea. We have a short report on it. You can go to my webpage. You can go to Steve Bellevin's webpage. But because these kinds of proposals are getting attention, I wanted to bring it to your attention, the kinds of issues. The kinds of issues we found with Ozzie's proposal is underspecified. Didn't examine the issue of this opening devices has to work across borders. And what do you do when the phone gets updated? It's one thing when Apple owns the whole stack. It's a completely different thing when you're looking at Android. I don't know, Roger hasn't said anything about time, so the two other things. At Tufts, we are looking for somebody in security, and for the fourth time, I'm running with Hillary Orman and Terry Benzel, GREPSEC, which is a meeting for women and underrepresented minorities in security and privacy, graduate students, and if there's room, undergraduates in May, just before Oakland next spring.
Okay, next we've got Becca.
I'm not actually speaking. Whoever is second on my laptop is speaking. Mike, I have yours as well.
Alright, so yesterday we were at our last supper, so I was having a lot of fun there. Nice food, nice drinks. And I went to the restroom and I met Pedro. And Pedro told me actually, hi Simon, you have to give a RAM sessions talk tomorrow. So I'm a very dramatic person, so I got in drama queen mode. And I went running to Carmela, who was having a beer. And she she told me, calm down, it's just 5 minutes. No, okay, but you have to be funny. So, got more wine. Or she told me, it could be also 2 minutes and not funny. So I'll try to be in the middle. Okay, so the less funny part. Okay, I met Pedro like 3 months ago, and Pedro knows a lot about the blockchain. I know a bit about statistical de-anonymization, so we thought it would be a cool idea to statistically de-anonymize blockchains. So as you know, the blockchain, Bitcoin blockchain has a lot of information about the user transactions, and there are a lot of anonymization tools proposed like CoinJoin, Bumblebee, and other cryptocurrencies like Zcash and Monero, and others that I don't know about. And there's a lot of papers de-anonymizing these things with a lot of information on how to do that. So what we want to do is we want to get heuristic from these papers and also information that is there in the blockchain to try to get a model, a statistical model of how users make transactions on the blockchain. So the good thing about having a model is that you can use it to de-anonymize whatever. You just plug this model into CoinJoin and you get an attack against CoinJoin. And same with other anonymization techniques, so we could actually compare between them as long as the model holds in practice, which is the most complicated thing. So the begging part is now, in order to evaluate this attack that we want to get, we need ground truth data, this de-anonymized data. For example, that has been de-anonymized because a user has published a set of keys or addresses, or using the IP address, or using cookies, as we saw this morning. So please, if you have some ground truth data and you're willing to share it, or you can point us out where to find this data, please contact me or Pedro and put in the conference, or drop us an email. And if you don't find us, you can also contact the mastermind behind this. Okay, thank you.
Mike's up next. After that, who's Bastion? I have questions. Very good. Sorry. Very good.
Awesome. So I'm very pleased to be here. My name is Ludovic, and I want to present you a traffic analysis resistant new anonymous communication network. So just to warn you, this talk has 2 parts. One that is a bit more serious, and then it's going to be easier. So your first reaction is, of course, why do we need yet another anonymous communication network? We have so many of those. And there is related work that was published this year at S&P that shows that the ICRC has a need for traffic analysis resistant secure communication. So just to expand a little bit on this, if you have an organizational network, like a LAN, it's very easy to eavesdrop upon it. Many entities like sysadmin, malicious or coerced users can see each other's traffic. If you encrypt, you still leak some metadata, for instance, the source and the destination, and more importantly, time packet series. I know I don't need to convince you, but just as an example, you can infer Skype, you can infer English words from Skype encrypted conversation. So this metadata is sensitive, of course, but here we are talking about the ICRC, which works in a high-risk scenario in conflict areas. So there is a risk for high-profile users in particular. And one tool that exists to remove this metadata leakage is our anonymous communication networks. They remove the source and the destination, and given sufficient padding, they also hide the time series of the packet, but they are not conceived for this setting. Essentially, all of them have a common characteristic, that is, they use several servers over the internet to route or mix the traffic, and security essentially comes from this set of servers. But that's not something we can easily remove. And I don't want to go into too much details here, but we can do better here. We have a solution that uses a DCNet. And it works like this. You have a building, say an ICRC delegation, you have clients, and what we do is deploy DCNet between the servers and the clients. This achieves the fact that clients become indistinguishable, and you have traffic analysis resistant channels connecting to the outside of the organization. So if you have an eavesdropper on the network, it becomes much harder to infer stuff. Let me skip to the last part of the talk. I gave you a little bit of technical details. My side of the version is I was simply in my office doing my stuff, my little project, and then the LCSC came in and said, oh, this looks great, can we test it? I was like, are you really sure? So this is going to happen. We're going to test something at the ICLC soon. Please try to review it and break it. I would be very happy to include some fixes. Thank you.
I have slides on this slide. Great. Carmela's repairing the browser. Roger, I don't think that microphone is working.
You push it on the bottom.
I can yell, but only if I know I need to. Oh my god. Okay. Discard this microphone. Oh, wait, it goes.
One microphone remains.
Okay, thank you. I'm gonna have a boring, unfunny talk, so I'll try to keep it short. My name is Bogdan, and I'm a PhD student at the PFL, and I'm working with Carmela. And I want to give a super brief teaser on our ongoing work about optimal defenses against web-safe fingerprint. And it's a joint work with Jamie from UCL and Nikita, who's our intern, and it's being stolen by Sergey Gilmon, shamelessly. So quick refresher, web-safe fingerprint is an attack that's mounted by a network adversary that takes a look at the packets and identifies which website a user is visiting. And our adversary is going to use a machine learning classifier, because machine learning is everywhere. And we're going to use Kumul classifier by Andrei Panchenko et al. So this classifier takes as input a network trace, it extracts certain features, Kumul features, and then runs SVM classifier, but we're going to simplify it and use just logistic regression. And what we're going to do to defend against this evil classifier is we're going to start with an existing trace, and we're going to modify it until the classifier is being fooled. We're going to do some transformations to it. And we're saying that what the defender can do is they can add dummy outgoing packets at any point in the trace. It can be many packets. Realistically, you can do more stuff, but this is one of the simple things to do. And then we're going to set a cost of a defense of a transformation, which is just the number of dummy packets that you add. Now, how we're going to find a defense is run an optimization procedure, which is going to minimize the cost of a transformation over all transformation until it finds the one that fools the classifier. And this might seem like a difficult optimization problem. And one way to solve it is just to do brute force. So go over all possible transformations of network traces until you find the one that fools it. But we found out that for some reason you can do it efficiently. Using heuristic graph search, I cannot go into details, but it's cool, and you can do it within seconds. So again, what you can do is to find the transformation that has the minimal possible cost in terms of edit dummy packets. So what I have time for, I guess, I'm not sure, probably, to show one of the results from the experiment that we had. So for example, here we're starting from an existing trace. So 1 is an outgoing packet, -1 is ingoing packet. And we're finding the transformation that fools the classifier by adding these dummy packets. So in this particular one, we added 9 dummy packets in total. There were 700 packets. We found this in 7 seconds. And it changed the confidence from 99% for a sensitive website to 53% for an innocuous website. So it kind of works. It's cool. So we can derive this lower bound for a defense. The problem is it's specific to a particular model. And so far, it only works for logistic regression. And the framework, another cool thing is the framework can be applied to other applications of machine learning discrete domains like malware or text. And if you want to talk about this more, and if you have any cool applications that you want to apply this to, then feel free to talk to me. I'm Bogdan. This is my email, and this is my Twitter handle, if that works. Yeah, thanks.
Okay, Jason is up next, plus mystery person that Jason has on his laptop, too.
Sí, hi.
We're on that one. Excellent, thank you. So what I do for my day job is I go into companies and I train them about privacy by design. Now, what I'm about to show you is a game that I've designed around this. For this audience, you may find it a little rudimentary and kind of high level, but you got to think the target audience here is web developers, software architects, lawyers, product managers, people who don't have a real good understanding around privacy. And it's a card game, and it is actually real. I do actually have cards. This is kind of a draft version, but I'm looking for feedback, any places where I could play this game, get people interested in it, any thoughts around it. So the basic idea here is that you have some information cards. So you have different types of information, and you play a set of 6 different information cards. And then you deal out some control cards to the different players. Each player gets 5 control cards. And they start playing from that. Now, you have to play the control cards in a certain order. You play them, you architect, secure, supervise, and balance the personal information. And you'll see as we go along how that goes. So the first thing is, so player 1 here plays an architect card where they're stripping unnecessary data from processing. So they get to turn over 1 card. Now they look at the different cards and they can see that ownership information is enhanced if it's found with computer device information, which that's here, and also demographic information is enhanced if it's found with ownership information. So the information kind of plays on each other that might increase risk. So they're going to hide or they're going to protect that ownership information. And then they play another card that summarizes data to reduce granularity. Now these control cards, and I don't see him in the audience, I think he walked out, but these control cards are based on Jaap Hink's strategies and tactics for privacy by design. So by summarizing information, we can turn over 2 information cards in the same category. Well, we have 2 tracking cards, we have 3 external cards. So we're going to choose to turn over some of the external cards. Next up, what happens is based on unprotected information, you end up getting privacy violations. So this is based on Dan Solov's taxonomy of privacy. So you have a secondary use violation, an intrusion violation, surveillance, and exposure. And then you go through and you continue, you supervise and you balance using control cards. So here we're going to maintain a good privacy policy and return 2 of the violation cards. So we're going to choose the 2 down below. And then we can balance the information, supply information about privacy risks, and return 1 of them. So we end up with 1 card left, and you see the +1 with external. Well, there's external data here, so we're going to end up with 2 consequences. So we get 2 consequences cards. Now there is actually strategy involved, and I want to show you this. So if we went back to this step, and where we turned over 2 information cards, we actually turned over the tracking cards, and then we move forward with that. Again, it's going this. What would happen is we could get rid of those 2, and since these are enhanced with tracking, but we no longer have tracking cards, then when we turn over that, we end up with 1 and 1 consequence. So then each of the players play in turn, and so this player ends up with 2 consequences. This one with 1, this one with 4. You turn them over and look at the consequences. So we have behavioral changes, we have social detriment, we have psychological consequences, economic loss, social detriment again, lost opportunity, lost liberty, and then each player tallies up how many points they had. This player had the most, had 4, so they're out of the game, and then they get to be the dealer the next round. So just to summarize, you start with personal information, you protect the information with data-oriented tactics, you use the unprotected information, you end up with potential privacy violations, you mitigate privacy violations with process-oriented tactics, and then for those unmitigated violations, you end up with consequences. So that's it. Like I said, any opportunity, if you see anything that this might be good for, please let me know.
Thank you. Serge is up next, and we're sort of disorganized, so if you're up after Serge, let me know. Great.
Okay. Well, I was going to go over, I guess to dovetail with some of the stuff that Joel presented, some of the correspondence we've received over the past year. So in Erwin's talk, we talked about looking at ad SDKs whose terms of service prohibit their use in apps directed at children. Here's an example of one such policy. So this is from a company, IronSource, that does behavioral advertising. It says the services are not directed to children under the age of 13, and children under the age of 13 should not use any portion of the services. So it seems pretty clear, right? If you're developing a kids app, you shouldn't put this SDK in it. So we got a letter from them informing us that we misquoted their privacy policy, and therefore our paper is wrong and there will be legal consequences. So specifically here it says that note that our privacy policy defines services as the platforms and services provided to third-party apps and websites. That is the implementation of our SDK and related services. Our terms of service emphasize that an app developer under the age of 13 is prohibited from signing up through our dashboard. And yeah, so they're claiming that, oh no, that policy only refers to developers under 13. They're making no claims about the users of their apps. So here is the privacy policy from at the point when we submitted the paper up until a week before they sent us the letter. So here it says that services, so this is, this has to do with, the end users' information when you view ads served by platforms and services operated by IronSource. So end users who are seeing ads in apps. Unfortunately, I guess they're not aware of the Wayback Machine or the idea that the internet is archival, because this privacy policy no longer exists. It was removed a week before they sent their legal letter to us. Moving on. Other correspondence we've had is reporting various data abuse. So here's another company, Tiny Labs. They have about 90 games in the Play Store. I think almost all of them are in the Design for Families program, which means that they are listed under the kids category and very specifically targeting children. We noticed that they collect a lot of different data types. So the Android advertising ID, which is permissible for advertising, but it's against Google's policies to collect that alongside other persistent identifiers. Say the Android ID, IMEI, serial number, phone number, email addresses, the Google Services Framework ID. They're also collecting various Wi-Fi information to map the user's location, as well as just the GPS location. I'll skip that. So CNET actually published an article about this once the paper was published online, and reached out to the developer for comment, who responded that their apps are not for children, and therefore they're not concerned with COPPA compliance. That's a non-issue. Here's their website. This exists today if you go to the website. You'll note that these are racing games for kids. Children love it. They feature simple controls that children love, and the levels are designed specifically for children. Absolutely. So we actually then, recently we reported them to Google for violating both the data abuse guidelines and various other of Google's policies. Google, 6 weeks later, responded saying that after conducting, after our report, after a thorough investigation of each of the apps that we highlighted in our research paper, the policy team did not come to the same conclusion that any of these 84 Tiny Lab Productions apps were violating COPPA in any way, and we do not consider these apps to be designed primarily for children. This, again, is their website.
What?
So, yeah, problem solved. Other correspondence that we've had, we've been working a bit with regulators. So we had a request from a regulator that was looking into location sharing. They wanted to know who the most prolific sharers of location data with advertisers were. So I queried the database, and to my surprise, we noticed that the CVS Pharmacy app, CVS is a major chain of pharmacies in the US, was sharing GPS coordinates with 40 different third parties. My first thought was this has to be a mistake. There's a bug in our code. So we looked into it, and it has to do with putting the GPS coordinates into the user agent string. So So the CVS app consists of several web views. It's almost entirely web views. This is, from the forgot password functionality, which loads a web view, which contains Twitter ads. And so, of course, any third-party content opened in any of these web views is now receiving the GPS coordinates. So I spent about an hour on CVS's website trying to find a technical contact to report this to. After an hour or so, I gave up and just sent it to the customer service. They responded promptly saying that we've reviewed your inquiry, but they don't share location or information with any third parties. So, case closed. Finally, a bit of a tangent. We've also been collecting privacy policies, though haven't really had much time to analyze them until now. The nice thing is, in the Play Store, developers, specifically if you're developing a children's app, you're required to submit a privacy policy. These appear as a link in a consistent location, so it's easy to screen scrape. And we've gotten a whole bunch of winners. Some of them are just very brief. Others create some impediments to viewing them. Here's one linked from the English language Play Store. This one, our privacy policy is fully COPPA complain, and then it goes on to describe practices that very clearly violate COPPA. This was also a good one. This game is primarily intended. This is their entire privacy policy. This game is primarily intended by use for kids 9 and younger and complies with known children's privacy statutes. So we've been posting a lot of these online on our blog. I invite you to take a look, or have suggestions for others that we could go into in detail on there. I've also tweeted about these on occasion, so I'll leave it at that.
Thank you, Serge. And Mike is up next. Who's up after Mike?
All right, good. Seems to work. So I'm Mike, and after the questions after Nick's talk on Tuesday about deniability, I'm gonna stoke this flame war. And how most flame wars go, the first thing you have to do is break your caps lock key. So, I'm going to take the position on this now. We need deniability in our protocols, and being a flame war, anybody who doesn't take that position, you're doing it wrong. And I blame you for what happened. For Trump being elected, it is your fault. We need deniability. If we had deniability, it would have been Hillary. And here's why. So if you might remember, Hillary's emails were leaked, and the DNC chair tried to make claims that they were modified or forged. However, tried to deny. They were leaked on WikiLeaks, and WikiLeaks decided to post some validation or a way to validate them. It turns out these emails, and pretty much all emails you send between your servers and Google's at least, have this DKIM verification so they can tell that it hasn't been modified in transit. WikiLeaks talks about how to verify this, and sure enough, with importing it into Mozilla, you get a nice little, yes, this is signed by HillaryClinton.com, so it could not have been forged. So she must have sent this email. And that was Trump's, one of his big platform issues, so you are the problem. An interesting thing, though, about what WikiLeaks reports on how to validate DKIM is the top part talks about, what DKIM is and how it does do validation. And then they have this little technical note here that says, well, in some of these emails, the DKIM doesn't validate, so maybe this is why. So they could have forged things. So, sometimes it's important, sometimes it's not. But another big issue on why we need deniability as well is if I want to have private communication with some of my friends about my president looking like an orange, I would use a secure messaging app, and to help protect my anonymity, I'm going to run it over Tor. But if the secure messaging app doesn't have deniability, it would do something very simple, like attach a signature to my messages. Now, the government who's trying to spy on me can check that that signature matches with my public key, breaking the anonymity provided by Tor. So this is a real problem and can get you put in serious trouble. One slight thing that I think we should try and do as cryptographers is to make a distinction. We are not legal judges. We should probably stop using the term judge in our proofs and start talking more in terms of distinguishers. Thanks for listening.
Thank you. And Justin is up next, and we have a set of people lined up from there. If you're in the rump session thing hoping to use slides and have not built a plan by now, consider building a plan.
All right, so this is just a preview of some work that I'll be presenting at CSET in a few weeks, and also just a general introduction to the Shadow Network Simulator. As the Tor Research Safety Board guidelines state, if you're experimenting on Tor, you don't want to do these experiments on the live Tor network because of potential privacy and security issues. So you need some sort of test platform to test them on. Shadow is one of, if not the most popular simulation platform for Tor. It's also useful for Bitcoin, and there's been some other applications that it's been used for as well. A few papers here have used Shadow in its in their experimental results. So yeah, if you're looking for something to do some kind of Tor experimentation on, that you don't have the resources to run, say, a bunch of Chutney instances or a full-on emulator for, Shadow is a really good option. Also, if you just want to do correctness testing, say, for some Tor modifications that you made, Shadow is a really good option for getting something larger, than like a Chutney network. So just some quick background on some of the things we changed. So originally in Shadow, there was this notion of changing, so there's these different hosts, each of which is running a Tor instance or a application instance that would swap out this application data using, sorry, to back up, Shadow allows you to run compiled source code. That's what its advantages over most network simulators. So if you have this source code, you compile it into a plugin. These plugins can be run in multiple instances by swapping out all the variables. Every single time you want to switch between executing this Tor relay and running another one, it'll swap it out. This led to a series of performance bottlenecks within Shadow. Blocking logging is an unrelated bottleneck, but also one that we ended up addressing. So some other bottlenecks as a result of this that we addressed are the cost of doing this data exchange every time you switch between hosts, the fact that you can't migrate hosts between worker threads. There was a lock on this libraries. Well, I guess you can't see here, but every single one of these, because you're compiling it to these plugins, and you're not compiling libraries on your system, this creates a global lock on any library accesses that Shadow was doing. So that's gone now. And then also because of the LLVM has to pull out all these variables, you can only compile it using LLVM, and also without any compiler optimizations. So the new design just creates a separate namespace. We used a custom dynamic loader to create separate namespaces. So this solves a lot of the issues that we were just talking about. Also some of the correctness issues where now there's a separate library instance for every plugin. So a couple charts. This is on the left side a small Tor instance with about 20 relays and 200 clients. And you can see we got up to 73% performance improvement. This is a larger Tor network on the right with let's see here, it was 700 relays with 20,000 clients, and also you can see a massive performance improvement just from the different things that we've changed along the way. So yeah, if you need some sort of Tor experimentation platform or just anything else that uses network code that you don't trust to modeling, say in NS3, then you should give Shadow a shot. If you tried it before and it wasn't fast enough or didn't work on your machine quickly enough, you can give it another shot now. It's considerably faster than it was before. And again, yeah, check out our paper in CSET coming up in a couple of weeks. Thank you.
Thank you, Justin. Sajun is up next.
All right. Hi, everyone. I'm Sajjan. I'm Ian's PhD student. So, hi. All right. So today I'm going to talk about our new advances in smartphone authentication. So phones have been around here for decades, but we still haven't been able to completely do good in the space of authenticating users against their own phone. So first, I'll just quickly skim through known ways of doing this user authentication for phones. Well, you have this traditional mechanism of PIN codes that predates even smartphones, where users have to remember their PIN code and they enter it in every time the phone needs to authenticate the user. More recently, with the advent of smartphones, we see these pattern unlocks where the users have to draw out intricate patterns to unlock their phone. The more intricate the pattern, the more security you get out of it. And even more recently, there's a lot of research going into the space called as implicit authentication, where users get authenticated on the background just based on their keystroke and their behavioral patterns. So they use parameters like the depth of the stroke, the length of the stroke, and the pressure applied, and all of these good parameters that contribute towards this. But just to give a better insight into all of this, here's a clear evaluation metric. We consider 5 metrics, and we say, okay, well, let's look at them and see how good these systems in fact are. Well, PIN and pattern are extremely inconvenient, that you get a prompt and then you have to do all of this manual labor. There's also this memory cost associated to it, that you have to take up some bytes of your brain to remember this PIN or this pattern. But on the other side, with implicit authentication, you have to do none of that since it's behavioral based. And meanwhile, there's also the concern of false negatives and false positives for PIN and pattern. In the case of PIN and pattern, there aren't any of these. But for implicit authentication, it so happens that an adversary who gets your phone might be able to do a few touches before they get locked out. Or on the flip side, you might get locked out for no reason whatsoever because you don't seem like yourself today. But most depressingly is the fact that all of these have been shown to be insecure. They're susceptible to all these shoulder surfing attacks and all sorts of attacks that you can train adversaries to do against yourself. So the real question is, where do we go from here? Well, fortunately for everyone, we at the University of Waterloo have been giving this a lot of thought. And we think we've solved this pretty well. Well, what can uniquely identify each user really, right? And so the answer is naturally DNA. So we introduce the lick lock. Well, all you have to do for the lick lock screen is you take your phone out and give a good nice lick across the middle of the screen, and thanks to the power of DNA testing, we can in fact assure that it is your phone and it is you who's using it. So here are some examples of our beta users who have been playing with the system. Here's another one and another one. And you'll notice that all of our users are surprisingly happy to be using the system. And here's why. Because we considered the fact of usability as well. I'm pretty sure no user would want to, get that filthy taste of plastic in their mouth for doing this authentication. And that's exactly why lick lock screens are available in chocolate, vanilla, and raspberry. Ew. And we're also working really hard to make sure that the flavor is consistent across multiple uses. So we're really looking forward to having this launched. Now to summarize, I introduced these 5 metrics earlier, and then we show you that lick lock in fact performs really well in all of these metrics. But not just that, we also add a new metric. And we promise you we're the only ones to do this really, really well. And thank you. With that, I will not be taking any questions.
And following up on that is George.
Hello, people. I'm George, and I work on Tor, and I'm here to present you 3 literature pieces from our team. I'm going to show you how to access them. I don't have slides. I will do this like sort of demo thing. You type this thing on the browser, blog.torproject.org, They're basically blog posts, you know? You can think of them though as like literature pieces. Oh, fuck. No. No. Okay. No demo. So what you do basically is visit the blog of Tor and check out the last 3 blog posts. They are of great interest. The third one is called Vanguards, and it basically presents a project, a small script we have to be used with Tor as an onion service or as a client, and will protect you against guard discovery attacks, which has been a class of attack. We've been. Thank you very much, Cecilia. Thank you. Ah, very nice. Okay, here we are, guys. This is the blog of Tor. Let's ignore this. Okay, here we are. Here is the first blog post. It will basically give you this add-on which defends against guard discovery attacks, and also does various other defenses and tries to detect various attacks that can be done by malicious clients, malicious rendezvous points, malicious actors in the network, basically. It's quite interesting. It has lots of heuristics and lots of actual defenses, and it would be great if people check it out. So this is one thing I want to show you. The next piece I want to show you is another good one. It's called Tor's Open Research Topics for 2018. It's basically a compilation of interesting research topics, from the performance side, better congestion control algorithms, how to turn Tor into datagram transports, how to improve performance with better load balancing, how to have better security against traffic analysis, how to have open usability issues we have, secure name system for onions. Basically, if you happen to be a researcher, it should give you a pretty good overview of what we're currently thinking about. And the third thing I wanted to show you is, these hard demos don't always work very well. Is this blog post by Chelsea, which is Chelsea Comlo, which is basically if you're a researcher here and you've been wondering why we didn't accept your 20,000 lines Perl script into Tor, this is basically a blog post that can give you some guidelines and some helpful instructions on how you can best interact with the team and make sure that your stuff gets accepted. It's written super well, and it's very useful for research teams, in my opinion. And it's basically a rundown of various guidelines you should follow to get accepted into Tor and also into many other open source projects. So this is what I want to talk to you about, and thank you very much.
Jeremy is on my list. Is he excited to go? Is now a good time? Awesome. Jeremy's up next. Stephen, Rachel, are you able to do after that?
Hi, I'm Jeremy. As we say in the US, I'm from the government. I'm here to help. Let's see. This is the least amusing, most lucrative talk you'll hear in the room. Okay, so for those of you who aren't familiar with the SATC or SATC program, it's the NSF's cybersecurity program. Funds about 200 new projects every year. There's a total of about 900 active research projects going on, including most of the presentations presented this week that are from US universities. Most were funded by the SATC program. I want to make you aware of some changes that are happening in the SATC program. The new solicitation for the next fiscal year actually came out this morning, and there are a few major changes. We're eliminating all deadlines. You can submit your proposals anywhere after October 1st, and we will process proposals periodically after they come in. You don't have to wait for a specific deadline. We're going to make sure the funding is evened out so you don't have a better chance or a worse chance depending when you submit. Submit when you're ready, not some artificial deadline. There's also a limit of one submission per fiscal year, that is October 1st through the following September 30th. And there's a new requirement for our medium proposals, which are up to $1.2 million, that you have to have a broadening participation in computing plan as part of any award. You don't have to have it as part of your submission, but you have to have it before you can get an award, and this is to increase the participation of women and minorities in the security and privacy research fields. For those of you who work with Israeli researchers, or those of you, if there are any in the room, who are Israeli researchers, there's also a program that's been ongoing for a few years that I want to make sure everyone is aware of, that you can submit a joint proposal to NSF and BSF, and you can get funding for the Israeli researchers out of BSF and for the American researchers out of NSF. I'm happy to talk to anyone who has questions about that. We're also talking to a few other countries about doing similar programs with their funding agencies. If you're an American researcher and you're not on the SATC announcements mailing list, you really should be, because that's where all this stuff gets announced, and you don't have to be so lucky as to encounter me to find it out. And let's see, last but not least on the subject of NSF, we are seeking a new program officer specifically working in privacy technologies. You have to be a U.S. citizen or working on U.S. citizenship, and you have to be affiliated with a U.S. institution. But if you're interested, we are definitely looking for someone effective immediately. And not related to my NSF role, but on my personal spare time, I do a scholarship program called Cleverly Scholarships for Women Studying Information Security. There are flyers over on the table. If any of you have students or any of you are students studying for bachelor's or master's degrees at U.S. universities, it is a scholarship program for you, and we're also looking for donors to help finance more scholarships. And again, I have to emphasize that part of it is not related to NSF. That's my spare time activity. Thank you.
Okay, Stephen and Rachel are up next. Is Xiao somewhere and ready? Or is Travis somewhere and ready? Travis is somewhere and ready. Okay, great.
Is Xiao here? Okay, he is actually, so.
Okay. So I was the sponsorship chair for PETS 2018, but from 2019 onwards, Rachel is joining, so welcome, Rachel. Sponsorship is very important to PETS. For those of you who were funded on a stipend, then the Ford Foundation and NSF were responsible for that. But the rest of the sponsors also allowed the registration rates to be at the level that they are, which if you look at things like CCS and Oakland, you'll notice they are much, much cheaper. And then that's partly due to all the volunteer effort that goes into it, but the sponsors also help. So many of the sponsors are here, so please do say hello and be nice to them. And you could be one of these sponsors too. So if your organization, institution, company might be interested in sponsoring PETS, then get in touch with me or Rachel and we can see what might be possible. Because you're at PETS, you might want to come to PETS 2019. If you are a sponsor of PETS, then you can use your organization's marketing PR budget to get you to come here, because the sponsorship comes with complimentary registrations from your organization. So that might be something that is useful to you, depending on how your budgeting works. Okay, so Rachel.
Yes, so yes, talk to us and give us your monies. I was speaking to Jeremy recently about the fact that the NSF sometimes has opportunities for building research community infrastructure, and we had a discussion in the town hall around data and code repositories and code reviewing, and I know that there are some people here that care deeply and passionately about this topic, and I want you guys to talk to me about coming up with a plan that is good and sustainable, and maybe we can, make it a reality. So, talk to me about that.
Okay. And then finally, I'm from UCL. There are quite a few of us here. like many places, we're always interested in growing the team. We're hiring at various places in the hierarchy, but I'm particularly interested in looking for a PhD student to work on anonymous collaboration technologies. This comes out of the idea that we know roughly how to do anonymous messaging, but people don't really want to use email anymore. They want to collaborate, Google Docs and so on. So how can you actually make this anonymous? If you're interested, then speak to me. There's details pinned to my Twitter profile, and the application deadline is the 5th of August. And finally, if you're interested in what else is going on at UCL, then our blog can be found here, benthamsgaze.org. Okay, thank you.
Great. We've got Xiao up next and Travis up after that.
Hello everyone, my name is Xiaofi Baochuan. I'm a PhD student from Drexel University under Dr. Rachel Greenstart, and today I want to talk about my research about measuring the value of online contribution made by anonymous users on Wikipedia. And for the introduction, as many of you might have known, like Wikipedia has systematically prohibited contribution from Tor users, and their reason is very simple. Like on their official website, they state that like they're afraid of vandalism. However, like Tor users still like trying to go above and beyond to contribute to Wikipedia, either by submitting a request for IP block exemption or like find a loophole to get into Wikipedia to edit. And we want to understand why would they want to do that. Like, are they like that determined to make a bad faith contribution, or like are they want to bring a meaningful content to Wikipedia like normal registered users? So our goal for the research is to first understanding the effects of policies and technologies designed to impede the anonymous users. The second goal is to examine and compare the contribution behavior of different groups of users on Wikipedia. I'm going to talk more about like the meaning of these goals and like how we like determine these goals. And based on the first two goals, we're gonna suggest some revision from Wikipedia to either change their policy or to build an infrastructure to support both anonymity seeking practices and efforts to control the abusive behaviors. So for the first goal, we look at the policy of Wikipedia, and we want to understand like how do they block Tor users. And we found out that like Wikipedia relies mainly on Tor block extension to block Tor users. However, Tor block did not work very well before 2014. And so many edit attempts to manage to get through from Tor exit nodes. You can see that like from February 2010 to December 2014, there are about like 13,000 edits made through, while from January 2015 to May 2018, there are only like less than 1,000 edits. So this is security flaw, like really negatively affect Wikipedia. Like did the edits from 2015 and onwards have better qualities than before that? We want to look at the revision quality of like these two time in order to figure out why. And next one, we look at the contribution behavior between two groups of users. The first one is the Tor users, and the second one is like the normal IP users, which are like not having an account. So like on paper, they look very similar. If they make an edit through on Wikipedia, like all we see is like their IP address, and we don't know the difference. So what makes Tor users having to suffer like from the block by Wikipedia, while like normal IP users don't? We're gonna look at two different things. The first one is the revision quality. As I said before, we want to determine the quality of each revision based on numerous factors. For example, the revision length, like the number of words like changed by each edit made by users. And the second one is the revision rate, which is like the how many percent of the edits were reverted eventually. And also, we dig deeper through the constant persistence, which is like how many words made in one edit actually stay until the current version of the article. And the last one is we use some machine learning method to determine whether or not an article was made like having good quality, or like they actually trying to make meaningful change, or like are they trying to vandalize the article. So the second thing we want to look at is the article qualities. We want to know like Tor users tend to look at the underproduced or overproduced articles and make changes in them. So what is underproduced or overproduced article? So underproduced article is basically any article that like a lot of people view but like have very, very poor quality, or like not yet have a good contribution, and overproduced is like exactly the opposite. So we want to know like do they care about like the less contributed articles, or like the one who already written very well. And that is currently what I have so far. Anybody who has any suggestion can like talk to me afterwards. Thank you very much.
Thank you. So we've got Travis coming up next, and Andrea, you can go after that. Awesome.
Okay. Awesome. Thank you very much. Hi, I'm Travis Mayberry. I wanted to give a short kind of supplement to our talk that we had one of the first talks at the conference. It was about TLS client certificate authentication. We kind of ended by just saying this is a really hard problem and we can't think of any solutions to it. A couple people have asked me about that, and I wanted to elaborate a little bit more and then open the question up to all of you very smart people. Maybe you can think of something that we weren't able to think of. So, refresher, why is this a problem? This is how TLS goes. If you want to connect to a website, you say client says hello, server says here's my certificate that proves who I am. Now you prove who you are. Client sends their certificate. At this point, encryption starts. This is bad because the certificate can contain things like your name, your email address, some other type of unique identifier. If somebody is watching, they can get all that information in the clear because the encryption doesn't start until after the client certificate is sent. Fortunately, there's a slight workaround for this. So Apache has implemented a thing in mod SSL where you can do this directive SSL verify client. What happens is the client says hello, the server says here's who I am, but it doesn't ask who the client is. It starts encryption right away, and then after encryption starts, it later on asks who the client is and renegotiates a new session. Now the cool thing about this is that it happens all encrypted now, so your certificate is safe. However, this is our attack from the paper earlier. What if instead you have an active attacker who can actually change the messages that are going back and forth? Client says hello, server says certificate. It doesn't ask for the client certificate, but the attacker can now inject this message, can say, hey, client certificate, give me one of those. Then on the way back, it will intercept that client certificate. Now, the whole reason this works is because this whole part of the conversation here is not integrity protected. Everything that happens before encryption is established is not protected by the TLS protocol. So we can inject messages freely. Now, here's some solutions that don't work. What did Apple do? So Apple changed their client software to not ever send unencrypted client certificates. This is great, but it literally pretty much only works for them because they control both the client and the server. They can make arbitrary changes, make up their own new protocols. They can deviate from anything however they like. If we have to abide by standards, then, well, we can use TLS 1.3, except that nobody does that yet. There are very few browsers that have it at all, oops, oh no, sorry. There are very few browsers that have TLS 1.3 at all, and even when they start to implement it, I can do the same thing that I just did there. If I have a malicious adversary, I can actually force you to use TLS 1.2. I can just pretend like the server doesn't support it, and you'll fall back onto that. So until we have completely deprecated and gotten rid of TLS 1.2, this problem will always exist. Now, another thing that some people do is let's move the client certificate exchange into a Java applet or something equivalent outside of TLS. The problem with that is it happens way, way too late, and I can still always just inject the certificate request before the applet even loads or anything happens on the client. So the problem is very built into TLS, and there doesn't seem to be anything we can do to fix it. Some things we've come up to mitigate with it are or include a setting in the browser that just won't let you transmit certificates in the clear, but this would break compatibility with pretty much every website that uses client certificates. We could give the user a warning when the certificates are sent in the clear. That's probably very unhelpful. Most users wouldn't know what to do with that. Does anybody have any better ideas? So if you do, please come talk to me after this. Okay, while I have 1 minute left up here, I would also like to announce that I'm at the U.S. Naval Academy, and we are hiring for tenure-track faculty positions in cybersecurity this year. We are actually looking for people in CS, electrical engineering, computer engineering, political science, law, anything that has to do with cybersecurity. We're looking for you. We're located in Annapolis, Maryland, very close to Washington, D.C. It's an undergraduate institution with focus on research. If you're interested in that or it sounds cool to you, talk to me or look for our announcement on the CFA. Thank you very much.
Andrea is up next, and is Damien around after that? I hope that's a yes. Yes, awesome.
All right, hello, I'm Andrea. I'm from Drexel University, and this is my very first PETS ever, so it's fantastic to be here. I come from a land called Kai. I don't know if anyone is familiar with this land, ACM Kai? Has anyone, yeah, okay. Has anyone ever actually been to Kai? All right, yay. How about CSCW? Getting a little more specific. All right, awesome. Okay, so thank you. I'm getting to know your community, and I wanted to know kind of what I was dealing with here. So you're a strange and wonderful group. You have a strange language that I'm just starting to learn, and I didn't know I was supposed to be funny. You also have a strange humor that I'm still catching on to. But I'm here because I'm actually collaborating with Rachel Greenstadt on some of the work that Chow talked about with the Wikipedia editing over Tor. So the approach that I take is very much human-centered. I talk to people. I look at the things, the texts that they produce, the images that they share, those kinds of things, and I try to understand what this can tell us about how they're thinking and what they're thinking and why they do the things they do. So I'm not so much looking at the Tor edits that get through to Wikipedia. I'm talking to the people who might be trying to edit Wikipedia through Tor. And so I've done a series of interview studies. I'm working on this now with my PhD student, Nora McDonald. And so we've talked to Wikipedians, we've talked to folks who contribute to things like open source and OpenStreetMap. And now we're doing a follow-up interview study talking to service providers. So we want to know, on the one hand, why are people interested in protecting their privacy and seeking out anonymity using tools like Tor when they're doing something like writing an encyclopedia article? What is the rationale there? How can we better support them? And on the other hand, what are the service providers thinking who may or may not allow edits from Tor, for example? What is their rationale? How are they thinking about this problem? And where are the facts? And so we have one paper out at CSW last year, hopefully another paper coming soon. And it's great to be here. So please come talk to me if you're interested in people. That's how I got up here. I said, Rachel, tell me, where are the people who want to talk to people? And she said, you should do a rump session talk. I said, interesting, a rump session talk. Turned out to be pretty cool. Thank you very much.
And actually, David is coming up before you.
So David will be next, and then we'll go to phase 2 of the sort of.
Does this mic work? I'd rather use this one.
We lost both of them. It's okay. We're up to that one now.
All right. Okay. Hello. All right. So I want to help redefine what this secure messaging problem is. I mean, it seems like historically cryptographers have focused on confidentiality, integrity of messages, but we leak a lot of metadata in all our communications. So we think that we should use mixnets to help us leak less metadata, and that we should also use Tor, and that possibly there's room for even a third architecture that would also benefit us. Let me think. So historically, mixed nets have had some obstacles like lack of funding, high latency, they were unreliable. So I think some newer mixed net designs that maybe you all are not aware of yet have essentially solved these problems. For example, the Lupix paper talks about how we can design pretty low latency mixed nets. And our provider model allows us to leak less information in the threat model for statistical disclosures, like intersection attacks and things like that. Does everybody know what a mixed-net is, actually? I think some people maybe don't know. All right, so one of the main, it's a so-called anonymity network, but what it is a message-oriented communications network where we can use latency and bitwise unlinkability between each hop in your route through the network, and use that, and also use decoy traffic and other tricks to hide metadata that we leak, like who is sending who a message, the size of their message, when they send it, the sequence of messages, their geographic location, things like that. For some people, geographic location is the most important thing to hide. For some other people, it may be something else. So there's many use cases, and this talk is too short to cover them all. Okay, 2 more minutes? All right. Let's see. We use the Sphinx packet format. It was invented by Ian Goldberg and George Genizis, and I think it essentially solves the problem that historically there were various exploits in packet formats, cryptographic primitives used, tagging attacks, things like that. One of the things that's underspecified in mixed net papers is they all assume there's like some PKI here that tells you about the mixed net and allows you, the client side, to come up with a path selection. So we've had to work hard to try to specify a PKI, and so we are essentially copying Tor's PKI, the directory authority system. Mixed Minion also serves as a good example of using that design. What else should I talk about? I have these cards I've written here. Let's see. So reliability is a tricky thing to get right. Like, we have a automatic repeat request protocol scheme, and we found that if it's implemented incorrectly, there's active confirmation attacks that you can do against a reliability protocol that you build on top of mixed nets. So I think that's good enough. Good for now. Thank you.
Does this mic work at this point? Yes. Yes, awesome. Okay, so that was it for phase 1 of the RUM session. Phase 2 of the RUM session involves people who will not be recorded. So now is the time to turn off the streaming and recording and so on. And I'll wait for some confirmation that we did. I saw that we're good. Okay, so now we have Damien coming up next.
And people should just probably stop live tweeting.
you
Thank you all for an excellent pets. Can you hear me? Good. Okay. This is sort of bittersweet for me and Damon because sharing pets has been a part of our lives for the last 2 years. And thank you guys for coming on this journey with us. But it's not like we're going anywhere. We're going to be part of this community moving forward. But we did not do this alone at all. Thank you for contributing to PETS as authors, hundreds of you, program committee members, 96 of them, many, many external reviewers who contributed a ton to our community. And you can see that even more than the program committee members, we had lots of external contributions. All the shepherds that made sure the papers were even better than they were submitted. And we had a proof reviewer to make sure that all of the cryptography was, up to spec. And thank you all for coming. This is one of the largest pets, I think the second largest pets we've ever had. And all of you that spoke, and our invited speaker, and all of you that volunteered to be session chairs and streaming session chairs to make this accessible to lots of people. So round of applause for everybody who contributed to this. But we have a really, really special thanks to, this is all the other things. Yes, This is also really special. Everybody is special. You are special, and you are special, and we're all great. Tariq and Susan, who put together the HotPets presentation, we are not done with this amazing week of privacy. There is still lots to come tomorrow, and you guys should all be excited about that. The Pet Award Chair, following this, there's going to be a reception about the Pet Award, and Matt and Ahmad put that together in terms of figuring out who should get the award. Our sponsorship chairs that have made this such a lovely event that did not cost arms and legs and various other organs. George and Stephen. And the stipend chairs who looked through all of the many, many deserving applications and helped many of you come here and be able to afford the trip. Emiliano, Roger, Nick, and Andre. Our publications chair, Mark and Philip, who made sure that all the LaTeX looked right and we all get, very nice De Gruyter official publications. And our liaison with De Gruyter, Matt Wright. Our video chair, Aaron Johnson, who is helped coordinate all of the lovely streaming and recordings that you guys are appreciating. Our web chairs, Ian Goldberg, who manages the submissions, and Kat Hanna, who manages the everything else web. Our publicity chairs, Kat Hanna and Wouter Lukes. The Best Student Paper Award, Paul Syverson, who kindly coordinated that selection. And a huge, huge thanks, this is the slide I thought was coming next, to Gemma and Griselda and Carmela, who was our liaison with them, who helped make the physical event and this experience in Barcelona so amazing, and all of the lovely receptions and dinners and breaks and delicious food. And Etikas, our hosts here in Barcelona. So and can I get a round of applause for all of you? And again, a huge thanks to our sponsors. At the platinum level, we had NSF, Zcash, and the Ford Foundation. At the gold level, Google. At the silver level, Brave and Comcast. And additional thanks to Orange and the Ajudament de Barcelona, and also the Tor Project, who is our fiscal sponsor. PETS 2019 is already in progress. Some people have already submitted to issue 1, and they will be finding out what happens about that as soon as they leave this PETS, basically. But not to fear, there are 3 more opportunities for you to be a part of the program next year at the end of August, the end of November, and the end of February. So get your papers in early, get your papers in often. And our organizers for next year, so Panos and Simone will be organizing our event in Stockholm, Sweden next year. They're going to come up at the end and tell us all about Stockholm, so I'm not going to get into that too much. So the program chairs, Damon and I are out. So in is Carmela and Costas, and they will be picking your program for next year. But I'd like to announce in 2020, Costas will continue, and Aaron Johnson will join him as our newest member of the program chair family. And we also have some people making decisions. Matt Wright is going to chair the award, and he will announce later on who will join him. Wouter is going to join Susan as a Hot Pets chair. Vasilios is going to join Philip as publication chair. Becca is going to join Kat as publicity chair. Ryan is going to take over for Aaron as video chair, and Aaron will help in that transition. I am going to take on the role of sponsorship chair. Our stipend chairs will remain the same, and so will our web chairs. So thank you to everybody who is continuing to make this conference happen. Also, in 2020, we are going to continue to hopefully have this event. And so you may have noticed that we are in Europe, and that next year we will be in Europe. And we love Europe, but in 2020 we would like to go to not Europe. So please consider making a proposal. Think about whether you'd be able to handle economic registration fees if you have a nearby airport, and if there's sort of a walkable setup. The proposals will be due September 28th to 2018. Send to Pet Board at Pet Symposium. If you are like, oh, sorry, there's no actual dash in Pet Symposium.
If that's what blocks them, it's okay.
Yeah. Talk to, or just, honestly, if you'd like to talk to me or any of the other organizers about what's involved in running pets, if you're like, that sounds cool to bring pets to my hometown or my university town, but I'm just not sure because that sounds like a lot of work. I've done it, and other people have done it, and we can kind of talk you through what it requires and help you with the proposal if you're really excited. If you are like, but I live in Europe, don't worry, like we will be back eventually, so like there'll be time to host pets in Europe, perhaps in 2021 or beyond. Next, I would like to bring up Paul to present the Andreas Fitzman Award in honor of one of the sort of founding members of our community, Andreas Fitzman, who hosted Pets in 2003 and was the instigator of the Pets Hike and always supported students and their work and the cause of privacy enhancing technologies, and really was one of the founding fathers of our field. He is unfortunately not with us, but we honor his spirit by supporting excellent work by students at Pets.
Yeah, Andreas, if you didn't know him, you missed something awesome. He was awesome, and he was very supportive of students, and so this is really fitting to give him this award. Give people this award in his name. I didn't know I was handing these out until about 10 seconds ago, so bear with me. So I'm doing these in a random order. So what we have is very nice certificates, one for each of the authors. Maybe in the interest of space for these big multi-authored papers, particularly we have since this is the student award, maybe just the student come up and hand them out to your co-authors at your convenience. So the first recipient is Privacy Pass, Bypassing Internet Challenges Anonymously by Alex Davidson, Ian Goldberg, Nick Sullivan, George Tankersley, and Philippa Valsordo. So. next up, we have Turtles, Locks, and Bathrooms, Understanding Mental Models of Privacy Through Illustration. Everybody has such long lists of co-authors, sorry. Maggie Oates, and names I'm not good at pronouncing. Yama Amadullah, Abigail Marsh, Chelsea Swopes, Shikun Zhang, Rebecca Balabaco, and Lori Craner. So. And one more. We also have Nomo Ads, Effective and Efficient Cross-App Mobile Ad Blocking by Anastasia Shuba, Athena Markopoulou, and Zubair Shafiq. So.
And thanks to Paul for coordinating the award selection. So there are more awards, and maybe we can all celebrate these awards and those awards and the Casper Bonin Award at the award reception, which takes place at, my Catalan is bad, but this place. And it will be supported by these people. And, and I'm really, really pleased to adjourn our lovely session, and thanks again to everybody who's here. You guys make pets so awesome.
Let's learn about Sweden.
Let's learn about Sweden. You guys all have to come next year. Sorry. I'm sorry. I forgot. Oh, we were? Just some. Is this not? It's not actually.
Ability for simultaneous interaction. Okay.
Oh, crap. Oh, we are. Okay, my PDF viewer is not working nearly as well as I was hoping. But because I don't know why. No, it's here. It's doing. It's not mirroring. Let's see if this works. Yeah, now I just need to grab this thing. There you go. Sorry.
It's okay. So all is well that ends well. So hello everyone. On behalf of Simon and myself, we are here to basically add some motivation for you to join us in Stockholm next year, or maybe reassure you on whatever concerns you might have. What I can say is that, well, if you have been in Stockholm in the winter, well, the summer Stockholm and the locals are totally different, much more fun. So the dates, as you see here, are pretty similar to this year's dates, and the idea is that we'll have exactly the same format and a little bit of, how to say, space, quote unquote, should there be any suggestion for a workshop that is before pets. There will be a hike, of course, there will be ice cream and so on. So everything as you know it. The only thing that might be missing is some of the locals, because this is a holiday season for the Swedes. But those that are interested, we certainly hope that they will make arrangements and they will be there. So, should there be some installation stuff? Not now.
Yep.
Right. So yeah. So I think that Saturday will be the hike, right? So. Yeah.
We included the hike day because some people couldn't stay for the hike because it wasn't in the dates, and now it is in the dates.
So,
It's an important part of the conference.
so basically, what you should expect when you come to Stockholm next year is that lots of fluent English-speaking people. That's it. All over. If you try to speak to them in Swedish, they will, unless you are a Swede or a trained in Swedish, they will switch to English to make your life easier. I think everything is quite nice. I mean, it's a beautiful landscape, a nice mix of nature and an urban setting. What probably might be an issue is, well, you might be wondering, is Scandinavia too expensive? Well, in some aspects it is expensive, but we'll make every effort to book or to block hotel rooms at very reasonable prices and have all sorts of suggestions for you so that you can save money or keep your budget as reasonable as you might need it to be.
And usually hotel rooms are cheaper during the summer, so it's different.
Yes, absolutely. So this
countries.
is the flip side of the Swedes being out of town. I mean, it's only tourists are there. So, is there any other? All right. So, of course, I mean, there is the academic background, but I guess you'll have time to discover this. So it's not only KTH. There are sorts of other, lots of other institutions there. Let me click. It's interesting from a technological point of view. Well, all right. Okay. So, and then the last comment that might be an issue for you traveling from far away. Well, there's a major international airport, but there are a number of other airports which you can use should you hop from another European hub, and this should make your flight very affordable in the end.
Yeah. Maybe to say, also check the weather forecast. So right now, actually, the temperatures are higher than here. So I think it should be around 34 degrees. But it could be also 12 degrees and rain. But now we have 34 degrees, so please check before that you're not surprised.
Yeah, absolutely.
That you have the warm clothes with
we
you.
cannot promise that the temperature
Yeah,
will be
but
the same
this
next year.
Summer we had a heat wave. Yeah.
Yes. So should you need anything while you're preparing for Stockholm next year, don't hesitate to contact Simone and myself at any point in time, and then we'll be happy to support you in any way we can. So thanks very much, and hope to see you all there next year.
And next, Matt's gonna give the talk about the Pet Award,
One more fake ending.
which I didn't realize.
Rats. Traffic analyzed. Okay. So later on this evening, we will be celebrating the various awards, but we don't necessarily have a microphone and so on. So this will be the time when we actually announce the award winners. This is the Casper Bowden Award for Outstanding Research in Privacy-Enhancing Technologies. This award is presented annually to researchers who have made an outstanding contribution to the theory, design, implementation,
or deployment of privacy-enhancing technology. It's awarded here at PETS each year, but the papers could come from any refereed venue, in this case from April 2016 through March 2018. It carries a cash prize as well as a physical award monument that will be shown in a minute. All right, so before we announce the awards, please indulge me just a couple minutes to talk about the namesake of the award and the process of selecting the winners. So first of all, you might be asking, why is this called the Caspar Bowden Award? So many of you know that answer, but many of you do not, so I'll go through that briefly. Caspar was a mainstay at the PET workshop, and then PETS as we know it now, and he was an active member of the PET board. He helped to build this community and this venue because he recognized the dangers and opportunities in our ever more technologically driven society, and he believed in privacy-enhancing technologies as a means to protect privacy and freedom from mass surveillance. Caspar was instrumental in creating this award and securing its initial funding. The award statue is sponsored by the Caspar Bowden Legacy Fund, and we named the award in his honor to recognize his influence and support of our work. Second, very quickly about the process for selecting the winners. We solicited nominations widely for the award and welcome contributions not only from the traditional security and privacy venues, but also from technology venues in other domains, and as well the social and behavioral sciences, since privacy is about protecting people. This year, 22 high-quality papers were nominated for the award. We had a committee of 14 members and 2 co-chairs. Ahmad Reza Sagadi could not be here today, unfortunately, but so unlike with a regular program committee, these papers had some degree already been vetted. They've been published in reputable venues, and so our committee members were not tasked to do the normal things of a program committee, but instead asked to understand whether these works were making a major impact in the research or practice of privacy. This is an impossible task to do and say you did it perfectly. Take 2 excellent papers that appeared in top conferences, one that was in cryptography and another that was in usability or law, and then say, well, which of these is having the most impact on privacy in the real world? And that's a very difficult thing to say. Fortunately, our excellent committee was up to the task, and thank you to those of you who are in the committee and those who are not here as well. They searched through the nominated works, identified a handful that really lived up to the standards of the award. And first, we are going to recognize 2 non-winning finalists in no particular order. How unique is your .onion? An analysis of the fingerprintability of Tor Onion services by Rebecca Overdorf, Mark Juarez, Ganesh Azar, Rachel Greenstadt, and Claudia Diaz. Come on up. I believe that 4 of the authors are here. You can come up and just be recognized. As you are being recognized, I'll also read out the other finalists. Improved Strongly Deniable Authenticated Key Exchanges for Secure Messaging by Nick Unger and Ian Goldberg. And I know Ian is here. Oh, and there's Nick. And there's Nick. Okay, great job with your papers. For them, that's a legit surprise. I'm not going to talk about your papers, though, so sit down. Okay, so those were 2 excellent finalists, but we also had our award winners, and the committee had actually 2 more very strong finalists, and committee members were arguing convincingly for both of these papers. So rather than cutting things on overly fine distinctions, we elected to award both of these deserving finalists with the top prize. These papers represent 2 different aspects of our field. One is more focused on elucidating an attack that we should seek to understand and try to prevent, and the other is more about the design of defenses. Well, without further ado, the first winner, again in no particular order, of the 2018 Caspar Bowden Award for Outstanding Research in Privacy-Enhancing Technologies goes to Reza Shokri, Marco Stronati, Kongzhen Song, and Vitaly Smadakov for their paper, Membership Inference Attacks Against Machine Learning Models. Congratulations.
So, congratulations. You take it first. So, I'm going to just tell you briefly about why we picked this as one of the winners. So, we all know how important machine learning is these days with the self-driving cars, smart home devices like Alexa and Google Home, and automatic language translation, and so much more. A very interesting direction is machine learning as a service, where the service allows you to upload some training data. It does the training for you, so it trains up a classifier, and you can put that classifier online to allow other people to classify some of their data. And that's great, but what happens if the training data is sensitive? So to use our sort of typical pets data example, what if you have a set of medical records for people who have this horrifying disease X? And then even knowing whether somebody is in the data set becomes a very sensitive piece of information. So what Reza, Marco, Kongzhen, and Vitali found out is very concerning. Not only are there attacks that can reveal membership in one of these data sets, but the attack works in the black box setting, which means that the attacker doesn't need to know anything about the classifier, just needs to be able to submit queries to it. And of course, in the machine learning as a service setting, that's exactly what's available to the attacker. So this paper, published at last year's IEEE Security and Privacy Symposium, has already had a major impact in the research world. It has 89 citations so far in just 14 months, representing works on privacy-preserving federated learning, differential privacy, and other privacy properties of machine learning models and training algorithms. So I think they are going to give some brief remarks and take it away.
First of all credit really goes to this guy, number one. Number two, if you want to learn more about amazing privacy issues and machine learning models, and disturbing, I hope, come to my Hot Pets talk tomorrow. I'm going to scare you even more. And three, on a more personal note, first time I got the Pet Award was exactly 10 years ago. Matt was the chair of the committee. So all I have to say, Matt, you should do this more often.
Thanks everyone. This is great. This is awesome. So Matt summarized everything very well. I would say that it's one of the main motivations that we had was to have a good way of measuring privacy in machine learning models. This is what I love to do, and this is great. Yeah, thank you very much. Yeah.
This will be hard to split, so you should decide what to do with it. Yes, so you can go ahead and step down. All right. The second, again in no particular order, winner of the 2018 Caspar Bowden Award for Outstanding Research in Privacy Enhancing Technologies goes to Rafael R. Toledo, George Denises, and Ian Goldberg for their work, Lower Cost Epsilon Private Information Retrieval.
I can shake your hand if you. All right, so again, I'll briefly just summarize why we picked this as one of the award winners. Private information retrieval, or PIR, is a way for people to get data from a server without revealing to the server which information they got. It has applications as a building block for privacy-enhanced versions of many technologies. An important example is certificate transparency. This is a technology for monitoring certificates, like the ones used for TLS to secure website connections, and to find attacks using compromised certificates. But it's a
potential privacy issue because you have to tell somebody, well, I went to this website and the certificate was this, in order to be able to test that out. So, unfortunately, despite a long line of research, PIR remains computationally expensive, and that has been a barrier to widespread deployment. The work of Raphael, George, and Ian, which appeared here at PETS in 2016, seeks to improve this. In particular, to paraphrase from one of the committee members, this work makes a basic theoretical and conceptual contribution by introducing epsilon PIR. This synthesizes two important but previously disparate areas of privacy, namely differential privacy and PIR. This is not only a theoretical contribution. It allows one to relax the usual assumptions of PIR to make more practical systems, and the authors examine different types of PIR systems. It also shows the application of these to a practical problem in a real, widely used system, namely certificate transparency. And so again, we'll invite them to come up and give some brief remarks.
Well, first of all, let's thank the committee for honoring us in that way. It is quite special to be recognized by our own community. I'll just say a couple of words because I think the summary of the paper was very excellent. I mean, there are two traditions when it comes to privacy technologies. There is the tradition that comes from hard cryptography, where you get very strong guarantees on what kind of security you can achieve. And then there is the tradition that comes more from the statistical side, from statistical disclosure to control to anonymity systems that are leaky systems, that we know we have to actually calculate how much they leak and kind of control for that. I guess the fundamental theoretical breakthrough of this paper is to say, well, what if we start building what we used to build using the cryptographic techniques that are usually providing an extremely high degree of assurance, more in the more statistical model. And therefore we can relax a little bit the security and hopefully gain a little bit in performance, which is very important because as it turns out that it is performance that makes things being rolled out and being practical and being ubiquitous. So we applied this to PIR, we applied then those kind of techniques to other systems, and in particular, once we start reasoning about leakage and non-negligible leakage in these systems, we can combine them with other techniques that also leak, such as anonymity systems, and compose basically all the leakages, and somehow we can have a more unified way of having PETs from these two traditions together. So once again, thank you very much. Of course, all the credit goes to the student that in fact did all the work, so thank you very much. Do you want to say a couple of things?
I would like to thank some member of the committee for awarding this paper. It was my first paper, and so I also want to thank a lot Ian and yes, I want to thank Ian and George for helping me and pushing me for this paper. It was not the easiest. I'm really grateful for being here today, and I don't have anything else to say that George hasn't said, so thank you.
All right, so is that actually the end? Are we actually at the end? Okay, so I'm going to declare that that's the end. Let's congratulate our winners one last time. Yes, I've been admonished to submit papers for the PET nominations for the PET Award for next year, which you will find the instructions to do that on the PET Symposium website. Tomorrow, yeah, don't do it right now. And that's it. So we will see you later tonight to have a drink of wine and say cheers to all the award winners.
you.